We exist on a fragile blue marble, suspended in a vast and silent ocean of stars, looking outward, forever asking the same profound question. Are we alone in this cosmic expanse? Is the intricate dance of life on Earth a singular, miraculous event, or is the universe teeming with possibilities? To answer this, humanity constructed a new eye, a golden sentinel, designed to peer back to the dawn of time and scrutinize the deepest cosmic shadows. The James Webb Space Telescope is more than an instrument. It is our species' collective ambition, a testament to our unyielding curiosity and our quest for understanding. It gazes into the infrared, seeing what was previously invisible. It senses the heat of nascent stars and the faint chemical whispers from distant worlds. And recently, this powerful eye turned its attention to a wanderer, a fleeting visitor passing through our stellar neighborhood from the cold, dark void between the stars. It was not a planet, nor a moon, but a comet named 3I Atlas, an interstellar object on a lonely trajectory through our solar system. Comets are typically predictable. They are ancient snowballs of ice, rock, and dust that sublimate under the sun's warmth, leaving a familiar, ethereal tail. But what the James Webb Telescope detected around this particular visitor was anything but familiar. It was a profound and perplexing scientific anomaly. Shrouding the comet was a mysterious cloud of gas, a chemical signature so unexpected it has sent ripples of intrigue and debate throughout the astronomical community. This gas did not match the typical composition of a comet's coma. It presented a chemical puzzle that mundane explanations have struggled to solve completely. When known physics and conventional models fall short, scientists are forced to consider possibilities that exist on the very edge of our understanding and imagination. And so, the ultimate question, however improbable, must be asked. Could this gas be something other than a natural phenomenon of this icy celestial body? Could it be a sign of something artificial? A technosignature left by an intelligence far beyond our own? A message in a cosmic bottle? This is the story of that observation, a journey into the heart of a cosmic mystery that challenges our assumptions about the universe and our place within it. We will dissect the data from our most advanced telescope, exploring the boundary where rigorous science meets the most profound questions of existence. Join us as we venture to the edge of possibility, to analyze the strange, ethereal clouds surrounding a visitor from an unknown star system. We begin by understanding our tool of discovery. The James Webb is not just another telescope, it is a quantum leap in observational power for humanity. Its 18 hexagonal, gold-plated mirrors form a light bucket of unprecedented size, capturing photons that have traveled for billions of years to reach us. This instrument was designed to answer the biggest questions. How did the first galaxies form? Where do stars and planets come from? And are we truly alone? Now, let us turn our attention to the object of this profound mystery. Comet 3I/Atlas, a designation that tells a story of discovery and origin. The I in its name stands for interstellar. This small, dark object is not from our solar system. It is a traveler from the deep, vast darkness. We have only ever confirmed a few such visitors. Each one is a precious, fleeting sample from another star's domain, offering clues about distant planetary systems. When astronomers pointed Webb towards this particular interstellar guest, they expected to confirm its composition, to see the familiar signatures of water ice and carbon dioxide. What they found instead was a ghost in the machine, a spectral signal that did not align with our extensive knowledge of cometary science and chemistry. The presence of this specific, unusual gas requires energy, a process to release it that is not easily explained by the gentle heating from our distant sun. This discrepancy is the very heart of the mystery. It is the grit of sand in the cosmic oyster that might, with time, produce a pearl of profound discovery. We must first approach this with scientific rigor, exploring all possible natural explanations, no matter how exotic they may seem to us. Could the comet have passed through a pocket of interstellar gas on its journey, collecting this material like a ship gathering seaweed from the ocean? Or does this comet possess an internal chemistry so alien, so different from our own system's objects, that it behaves in ways we have never before witnessed? Perhaps its core contains radioactive elements, providing an internal heat source that drives chemical reactions not powered by the star it is passing. These are the leading naturalistic theories, each being tested against the precise data gathered by the Webb telescope's sensitive instruments. But after exhausting the probable, science permits us to contemplate the improbable. The data is the data, and it demands an explanation. What if the gas is not a product of the comet itself, but a byproduct of something else? Something the comet is carrying, or something it is. The term alien is loaded with cultural baggage. In science, we might refer to it as a biosignature, or more provocatively, a technosignature. A biosignature would be a gas produced by life, even microbial life. Methane on Mars is an example of a potential, though unconfirmed, biosignature. A technosignature is even more profound. It implies not just life, but intelligent, technology-creating life. It is the exhaust of a civilization. Could the anomalous gas surrounding 3IAT-LAS be the venting of a fuel source, the remnant of a propulsion system from an interstellar probe? This is the most extraordinary of all possibilities, and extraordinary claims require the most extraordinary and undeniable evidence to support them. We are not there yet. What we have is not evidence, but a tantalizing mystery. A single, strange data point in the cosmic ocean. The scientific process is now in full motion. Teams around the world are modeling scenarios, reanalyzing the spectra, and searching for alternative explanations. This single observation could reshape our search for extraterrestrial intelligence, guiding us to look not just for radio signals, but for chemical anomalies on passing objects. The universe is under no obligation to make sense to us, or to conform to our limited expectations of what is natural and what is not. Every great discovery in astronomy began as an anomaly, a piece of data that didn't fit the current model, from the discovery of Uranus to the expansion of the universe. This mysterious gas cloud may eventually be explained by a new, but entirely natural chemical process we had not yet conceived of. Such a discovery would in itself be a monumental step forward, deepening our understanding of the complex physics governing the cosmos and its many worlds. But the other possibility, however remote, lingers in the back of every scientist's mind, a quiet whisper that motivates the entire endeavor. The possibility that we have stumbled upon a signpost, a deliberate or accidental marker left by another intelligence in the vastness of interstellar space. This is the nature of true exploration. We are not just mapping the stars, we are mapping the boundaries of what is possible. So let us now journey deeper into the data to understand the science behind this detection and weigh the evidence for ourselves on this cosmic voyage. To truly comprehend the significance of this discovery, we must first appreciate the instrument that made it possible. The James Webb Space Telescope is not merely an optical device. It is a time machine and a cosmic chemist. Orbiting at the second Lagrange point, 1,000,000 miles from Earth, it maintains a frigid operating temperature below -220 degrees Celsius. This extreme cold is essential to reduce its own infrared noise, allowing it to detect the faint, ancient heat signatures from the universe's most distant objects. Its primary mirror, a vast honeycomb of gold-coated beryllium, gathers light with unprecedented sensitivity, focusing these whispers from the void onto a suite of hyper-advanced scientific instruments, each designed to decode the universe's fundamental secrets. The crucial technique used in this investigation is spectroscopy. In essence, this process treats cosmic light as a message, a detailed letter from a distant source. When Webb's instruments pass this light through a prism or grating, it unfurls into a spectrum, a rainbow of infrared colors. But within this rainbow are dark or bright lines, specific frequencies that have been absorbed or emitted by atoms and molecules. Each element, each compound, has a unique spectral barcode. By reading this barcode, astronomers can determine with astonishing precision the chemical composition, temperature, and density of stars, galaxies, and the atmospheric haze around comets, even those that have traveled for millennia from an unknown home. Webb's near-infrared spectrograph, or NIR-SPEC, is the specific tool that unraveled the mystery of 3I/Atlas. It is a masterpiece of microengineering featuring a remarkable device called a microshutter array. This is a grid of 250,000 tiny shutters, each no wider than a human hair, which can be opened or closed individually by the ground control team. This allows the instrument to isolate the light from a single specific target, in this case, the faint interstellar comet, while blocking out the contaminating light from brighter background stars. It is this surgical precision, this ability to perform a chemical biopsy on a fleeting cosmic target, that allowed Webb to capture the anomalous spectral signature that has so captivated the scientific world. Based on decades of studying comets born within our own solar system, a clear and predictable spectral profile has emerged. We expect to see the strong absorption lines of water ice, the primary component of any cometary nucleus. As the comet warms, this ice sublimates into a gaseous coma, and we then detect the clear signatures of its vaporous form, H2O. Alongside water, we find frozen carbon dioxide and carbon monoxide, which vaporize at even colder temperatures. We also frequently observe simpler organic molecules, like methane and ammonia, the basic building blocks of prebiotic chemistry. This well-understood chemical cocktail is the established baseline, the control sample against which all new cometary observations are measured. It is the known, familiar chemistry of our own cosmic backyard. When NIR-SPEC delivered its data on 3I/Atlas, the expected signatures were present, but they were accompanied by a ghost in the data, a prominent spectral line that was profoundly out of place. The analysis revealed an unexpectedly high concentration of a complex hydrocarbon, specifically ethylene glycol, a molecule commonly used on Earth as antifreeze. While simple organic molecules are common, a molecule of this complexity, in this abundance, has never been seen in a cometary coma. It is a diol, an organic compound containing two hydroxyl groups, suggesting a much more complex chemical history than the simple freeze-out of gas in a protoplanetary disk. It hints at chemical processing, at conditions of formation that are entirely alien to our experience. The core of the scientific puzzle is one of energy. The chemical bonds within a molecule like ethylene glycol are strong. To liberate it from the icy matrix of the comet's nucleus and release it into the coma in such quantities, a significant energy input is required. The faint warmth of our Sun, at the vast distance 3I/ATLAS was observed, is simply insufficient to explain the phenomenon. The solar energy budget does not add up. This is not like watching ice sublime into water vapor on a warm day. It is like finding liquid water on the surface of Pluto. There must be an additional unknown energy source at play, either from within the comet itself or from a process we have yet to comprehend. This leads us to our first major naturalistic hypothesis. 3I/ATLAS was born in a truly alien solar system with a profoundly different chemistry. Our solar system formed from a nebula with a specific ratio of elements, mostly hydrogen and helium, with trace amounts of heavier elements like oxygen, carbon, and silicon. But other star systems can be dramatically different. Imagine a star system that formed from the remnants of a carbon star, a nebula exceptionally rich in carbon and complex organic compounds. In such a cradle, it is plausible that more complex molecules, like the one Webb detected, could form more readily and become integrated into the icy bodies that coalesce in its outer reaches. In this scenario, 3I/Atlas is not strange. It is simply a messenger from a different chemical paradigm. If we accept this hypothesis, we can begin to paint a picture of the comet's origin. It would be a place of cosmic abundance, a stellar nursery seeded by the final, carbon-rich exhalations of a dying star. The planets forming there would not be like our own. Instead of silicate rocks and water oceans, you might find worlds with crusts of diamond and graphite, with rivers of liquid methane flowing under a thick, smoggy orange sky. The comets, the leftover building blocks, would be less like water ice snowballs and more like frozen balls of complex tar and organic soup. This interstellar visitor, then, provides us with a precious, tangible sample of such a system, a piece of evidence that such exotic chemistries are not just theoretical but are real and drifting between the stars. However, this compelling narrative of an exotic origin faces its own scientific hurdles. Even within a carbon-rich protoplanetary disk, a significant energy source is still required to synthesize a molecule as complex as ethylene glycol from simpler precursors. Furthermore, such a complex molecule is more fragile. Over the eons of its journey through interstellar space, it would be subjected to the constant, sterilizing bath of high-energy cosmic rays. These particles should, over millions of years, break down such complex molecules into simpler, more stable forms. The fact that this gas is present now, in such abundance, suggests it was either incredibly well protected deep within the nucleus, or it was released by a very recent, ongoing process. The alien chemistry hypothesis, while elegant, is not a perfect fit. This pushes scientists to consider a second natural possibility. The comet possesses its own internal engine. The source of this engine would be the decay of radioactive isotopes trapped within its core. When stars die in supernova explosions, they enrich the surrounding space with freshly forged, unstable elements. If the cloud that formed 3 IATLAS was seeded with a high concentration of these isotopes, such as aluminum-26, their slow radioactive decay over millions of years would generate a steady, gentle heat from the inside out. This internal warmth could be enough to create a subsurface layer of liquid, a chemical reactor driving complex reactions and pressurizing gases that are now venting into space as the comet's surface is disturbed by its passage through our system. The internal heating model is certainly plausible, as evidence for it exists within our own solar system's history. It is thought to have played a role in the differentiation of asteroids and the formation of subsurface oceans on moons like Europa and Enceladus. The challenge, however, is matching this mechanism to the specific chemical signature observed by Webb. The byproducts of radioactive decay and the subsequent chemical reactions are generally predictable. They do not typically result in the preferential production of a complex organic molecule like ethylene glycol. For this theory to hold, the comet's initial composition would have to be exquisitely tuned in a very specific way, making it an object of extreme rarity, an outlier in a cosmic chemistry set. The explanation is possible, but it may not be probable. Here we stand at the frontier of scientific inquiry, where known physics meets an unknown phenomenon. The process is one of meticulous elimination. Every photon captured by the James Webb Telescope from this object is a clue. Scientists are constructing complex computer models, simulating the comet's journey through the interstellar medium to see if it could have picked up this gas along the way. They are recreating the conditions of a radiogenically heated core in simulations to see if any plausible chemical pathway leads to the observed result. They are pushing the boundaries of our understanding of astrochemistry, all in an attempt to find a natural explanation that perfectly fits the strange and beautiful data returned from the void. Let us examine the trajectory of 3 IATLAS for more clues. Its path was calculated with extreme precision, tracing its journey back into the interstellar darkness. If it had recently passed through a dense molecular cloud or a stellar nebula rich in organic compounds, it could have acquired a surface layer of this material, which it is now shedding. However, the trajectory analysis shows no such recent encounter. For at least the last several 100,000 years of its journey, the comet has been traversing the local interstellar cloud, a region of space that is incredibly diffuse and lacks the density of complex molecules needed to explain the observation. The flypaper hypothesis that the comet simply collected this gas seems increasingly unlikely. We can also analyze the physical properties of the gas cloud itself. The way the coma expanded from the nucleus, its temperature, and its density distribution all provide crucial information. A natural outgassing process, driven by solar heating, tends to be uneven, often occurring in jets from active regions on the comet's surface as they rotate into sunlight. The gas cloud detected by Webb, however, was remarkably uniform and symmetrical, almost as if it were being released gently and consistently from all directions. This morphology is difficult to reconcile with the sublimation process tied to the sun's warmth, suggesting a release mechanism that is more controlled and independent of the comet's orientation in space. Another avenue of investigation involves looking for other, associated molecules in the spectrum. Chemical reactions rarely produce just one product. If a specific natural process were creating the ethylene glycol, we would expect to see other associated byproduct molecules in the data. The search for these corroborating signatures in the faint noise of the spectrum is a painstaking process. So far, this search has come up empty. The dominant, anomalous signal appears to be strangely isolated, without the expected chemical siblings that would point to a specific formation pathway. This absence of evidence, while not conclusive, is itself a piece of evidence that challenges the conventional models. Consider also the comet's brief history of observation since its discovery. It did not exhibit the typical behavior of a comet approaching the Sun. There was no dramatic brightening as it warmed, no development of a significant dust tail. It remained a faint, dark object, with its activity dominated by this strange, invisible, gaseous halo. This passive behavior suggests that the process releasing the gas is not a runaway thermal effect, but something more stable and perhaps internally regulated. It is another subtle clue that points away from the familiar, chaotic nature of cometary sublimation and towards a mechanism that is both more controlled and more mysterious. The scientific community thrives on such puzzles. This is not a moment of crisis, but of opportunity. An observation that defies easy explanation is a signpost pointing towards new physics, new chemistry, or a new understanding of the universe. Every major paradigm shift in the history of science has been precipitated by an anomaly that refused to be ignored. From the peculiar orbit of Mercury, which led to general relativity, to the cosmic microwave background hiss that confirmed the Big Bang, progress is born from data that breaks the existing mold. The strange gas of 3I/Atlas is the latest in this noble tradition of cosmic conundrums. We have now explored the most plausible naturalistic explanations and found them wanting. While one of them may yet be proven correct with a new insight or model, their current shortcomings force us, as rigorous scientists, to consider the alternative. When the data persistently refuses to fit within the box of known natural law, we must entertain the possibility that we are looking at something that does not belong in that box at all. We must open our minds to the hypothesis that the gas cloud surrounding 3I/Atlas is not a product of nature, but a product of intention. We must, with caution and intellectual rigor, confront the possibility of an artificial origin. To contemplate an artificial origin is to enter the realm of technosignatures. A technosignature is any observable, measurable evidence of technologically advanced life. For decades, our search has been dominated by listening for radio signals, a method we call SETI. But the James Webb Telescope has opened a new front in this search. We can now hunt for evidence not just in the electromagnetic spectrum, but in the chemical composition of the cosmos itself. We can search for industrial pollutants in the atmospheres of exoplanets, for the heat signatures of massive astroengineering projects, or, in this case, for the chemical exhaust and material residue of an interstellar vehicle. If 3I/Atlas is indeed an artifact, what could it be? Given its small size and trajectory, it is almost certainly not a generation ship or a colony vessel. The most logical conclusion would be that it is an unmanned probe, a robotic explorer sent from another star system, similar in purpose to our own Voyager or Pioneer spacecraft. It might be a vessel of pure exploration, sent to gather data. Or perhaps it is a Bracewell probe, a messenger designed to wait patiently in a star system for a native intelligence to arise and discover it. The gas in this context could be the result of its slow degradation over a journey that may have lasted for millions of years. Let us explore this probe hypothesis further. An interstellar vehicle would require a power source for its long journey. Perhaps what we are observing is the slow venting of a degraded coolant from a nuclear fission or fusion reactor that has long since gone cold. Or it could be the byproduct of a decaying power source, a chemical signature of its slow death. The uniformity of the gas cloud could be explained by a slow, steady leak from a compromised containment vessel. The specific molecule of ethylene glycol is even tantalizing in this context. On Earth, we use it as an antifreeze, a substance crucial for regulating the temperature of machinery in extreme cold, a purpose it could certainly serve on an interstellar craft. Another fascinating, albeit more speculative possibility, is that the gas is related to a propulsion system. While our own chemical rockets are primitive, advanced physics allows for more exotic concepts. Perhaps the gas is a remnant of a Bussard ramjet's exhaust, or a reaction mass from a fusion engine that was used for deceleration or course correction millennia ago. The chemical composition might seem strange to us, because it is the byproduct of a physics we have not yet mastered. In this scenario, the James Webb Telescope did not just find a chemical anomaly. It found the fossilized ghost of an engine far more advanced than anything humanity has ever conceived. We must also consider the most profound possibility, that the signal is intentional. A radio beacon requires a receiver to be listening at the right time and the right frequency. But a chemical signature is a passive, persistent message. Any civilization that develops spectroscopy and begins to analyze the objects passing through its solar system would eventually find it. It is a brilliant, patient way to announce one's existence. The specific molecule could be a calling card, a chemical chosen for its unnatural abundance, designed to pique curiosity. It could be the first part of a larger message, a cosmic hello, written in the language of molecular chemistry. The confirmation of 3IATLAS as an artifact would represent the single greatest discovery in human history. It would definitively answer the question, are we alone, with a resounding no. The philosophical, societal, and religious implications would be staggering, forcing a complete re-evaluation of humanity's place in the cosmic order. It would instantly transform us from a species that feels alone in the universe to the newest members of a galactic community, a community whose existence we have only just detected through the faintest of ancient whispers. The knowledge that intelligence has not only arisen elsewhere, but has mastered interstellar travel, would change everything. Scientifically, it would ignite a revolution. The object itself would become the most precious artifact in existence. Every scrap of data from Webb would be reanalyzed with an intensity never before seen. It would launch a new golden age of astronomy and engineering, as humanity would undoubtedly marshal its resources to attempt an intercept mission for the next such object that enters our system. The study of its materials, its design, and its chemistry would offer technological insights that could leapfrog our own science by centuries or even millennia. It would be our first direct look at a technology born under another sun. The discovery would also force us to confront a concept known as the Great Filter. This is the idea that there is some barrier or challenge that prevents life from progressing to a spacefaring, multiplanetary civilization. The fact that we have not yet seen widespread evidence of alien life suggests this filter may be very real. Is it the jump from non-life to life? From simple cells to complex intelligence? Or is it the development of technology that inevitably leads to self-destruction? The existence of an interstellar probe would be a profoundly hopeful sign. It would mean that at least one civilization, somewhere, somehow, made it through the filter. It would mean that survival is possible. What could we infer about the nature of the intelligence that sent it? The object's likely age suggests a civilization far older than our own. Their motivations would be entirely unknown. Were they explorers, conquerors, or artists? The probe's inert, passive nature might suggest a peaceful, scientific purpose. Perhaps they are biological beings like us, or perhaps they have transcended biology, becoming a civilization of pure machine intelligence. The probe itself might be intelligent, a sentient artificial mind that has been silently sleeping as it coasts through the dark. The questions raised by its existence would be as vast as the space it crossed to reach us. This object, whether natural or artificial, highlights a fundamental truth. The universe is unimaginably vast and old. Countless star systems have existed for billions of years longer than our own sun. The opportunity for life to arise and evolve has been present in our galaxy for eons before Earth was even formed. From a purely statistical standpoint, the existence of other intelligences is not just possible, but probable. The challenge has always been the immense distances that separate the stars, a barrier of space and time. 3I/Atlas, in its fleeting passage, has reminded us that this barrier is not insurmountable. The void can be crossed. The very act of this search elevates our species. To build an instrument like the James Webb Space Telescope, to launch it 1,000,000 miles into space, and to use it to scrutinize a faint speck of light from another star system is a testament to the power of human curiosity. It is an expression of our deepest desire to know, to understand our origins and our destiny. Whether we find new laws of chemistry or the relics of another mind, the quest itself gives us purpose. It is the modern equivalent of the great voyages of discovery that once mapped our own planet. But now the ocean is the cosmos, and the islands are the stars themselves. It is crucial, however, to return from these profound speculations to the bedrock of the scientific method. At this moment, we do not have proof of an alien artifact. We have an anomaly, a beautiful, deeply intriguing, and persistent anomaly. The ethics of science demand that we exhaust every possible natural explanation before we can even begin to claim an artificial one. The burden of proof for such an extraordinary claim is, and must be, incredibly high. The data is tantalizing, but it is not yet conclusive. The process of verification, of peer review and further observation is the slow, steady, and essential heartbeat of scientific progress. The ultimate confirmation would require observing another, similar object. This singular detection is a potential discovery, but a pattern of them would be proof. Telescopes around the world, both on the ground and in space, are now on high alert. Surveys like the upcoming Vera C. Rubin Observatory are designed to scan the entire sky every few nights. They will be able to detect interstellar objects with unprecedented efficiency. When the next visitor like 3I/Atlas is spotted, you can be sure that the James Webb Telescope and every other major observatory will be immediately directed towards it, ready to perform a rapid response chemical analysis to see if this anomaly repeats. This entire event underscores the irreplaceable value of flagship science missions. The James Webb Space Telescope took decades of work, immense resources, and the dedicated effort of thousands of people from around the globe to design, build, and launch. Its power and sensitivity are what allowed it to be in the right place, at the right time, with the right tool, to capture this fleeting phenomenon. It is a powerful reminder that exploration requires investment in bold, ambitious projects. Discoveries of this magnitude are not made by accident. They are made possible by the patient and visionary construction of new windows onto the universe. The story of 3I/Atlas is also woven into the larger tapestry of Webb's primary mission, the characterization of exoplanets. The same spectroscopic tools being used to analyze this interstellar comet are also being used to scan the light that passes through the atmospheres of planets orbiting other stars. The ultimate goal is to find a biosignature, the chemical fingerprint of life, on one of those distant worlds. Whether it's the methane from microbes or the oxygen from alien photosynthesis, the search is the same. It is the grand quest to find worlds that, like our own Earth, harbor the miracle of life. Our solar system is a dynamic, moving place. We are constantly passing through streams of interstellar dust and gas as we orbit the center of the Milky Way. Objects like 3I/Atlas are not a rare invading force. They are part of the cosmic environment through which we are perpetually traveling. We now understand that our solar system is not an isolated island, but an open ecosystem, constantly exchanging material with the vast interstellar medium. This realization changes our perspective, suggesting that the building blocks of life, and perhaps even life itself, may be far more widespread and easily transported across the galaxy than we ever imagined. In the end, we are left with the elegant principle of Occam's razor, which suggests that the simplest explanation is often the correct one. At present, the simplest explanation is not alien technology, but a gap in our own knowledge of astrophysics or astrochemistry. It is statistically more likely that we have discovered a new, rare, but entirely natural type of cosmic object, a cometary class we have never seen before. This would be a monumental discovery in its own right, forcing us to rewrite textbooks and expand our models of how solar systems form and evolve. This is the most probable and still a wonderfully exciting outcome. Yet, the power of this mystery lies in the fact that the alternative, however improbable, cannot be entirely dismissed. The data from the James Webb Space Telescope has opened a door that was previously locked. It has presented us with a legitimate, evidence-based reason to consider a technosignature. This is a significant step beyond pure speculation. The conversation is no longer just the domain of science fiction, but is now happening in the peer-reviewed journals and conference halls of mainstream astronomy. The search for extraterrestrial intelligence has gained a powerful new tool and a tantalizing new piece of evidence to ponder. The comet itself is now gone. It is receding from our sun, already having passed the orbit of Saturn, on a journey that will take it back into the unending night between the stars. It will likely never return. We had one brief chance to observe it, a fleeting encounter on a cosmic scale. This makes the data collected by Webb all the more precious. It is a single frozen snapshot of a profound mystery, a postcard from the void. All the answers we seek must be teased out from those few hours of observation, from the faint infrared light it shared with us before it departed forever. The search for life beyond Earth is fundamentally a search for ourselves. It is an attempt to understand our own context within the grand cosmic narrative. Are we a fluke, a beautiful but lonely accident in a sterile universe? Or are we a part of something much larger, a vast biological and intellectual tapestry woven across the stars? Each new piece of data, from the organic molecules in meteorites to the potential oceans on distant moons, and now to the strange gas of an interstellar wanderer, brings us one small step closer to answering that ultimate question of our place in the cosmos. This journey of discovery requires a unique blend of open-minded imagination and rigorous, skeptical analysis. We must be willing to imagine possibilities as wild as interstellar probes and alien messages, because the universe is often stranger than we can imagine. But we must also be unflinchingly critical of our own data and our own biases, ensuring that our conclusions are built upon the solid foundation of evidence, not upon our hopes or desires. It is in the delicate balance between these two modes of thinking that true scientific progress is made, and where the greatest discoveries are waiting to be found. The story of 3i/Atlas is a perfect illustration of how science works in the 21st century. It is a global, collaborative effort. The James Webb is an international partnership. The data it collects is shared with scientists around the world, each bringing their own expertise to bear on the problem. From astrophysicists to chemists, from data scientists to engineers, thousands of human minds are now focused on this single, faint object, working together to unravel its secrets. This collaborative spirit is humanity at its very best, united not by borders or beliefs, but by a shared, passionate curiosity. Let us not forget the sheer beauty of the object itself. Lost in the technical data and grand speculation is the simple fact that a visitor from another star graced our solar system with its presence. For millions, perhaps billions of years, it traveled through the silent, cold dark. Then, for a few short years, it passed through our small, well-lit neighborhood, was seen by us, and then continued on its way. There is a profound poetry in this celestial encounter, a brief intersection of two incredible journeys, that of the comet and that of our own species, which had evolved just in time to build an eye powerful enough to see it. This discovery also forces us to think on truly astronomical timescales. The civilization that might have launched this probe could have risen, flourished, and vanished hundreds of millions of years ago. We could be looking at the last relic of a long-dead culture, their final message only now reaching us. Like the light from an extinct star, this adds a layer of solemnity and grandeur to the mystery. We are not just looking for our contemporaries, we are engaged in a form of cosmic archaeology, searching for the faint ruins of ancient galactic empires among the stars. Ultimately, the mysterious gas cloud around 3i/Atlas may serve as a cosmic catalyst. It will undoubtedly inspire a new generation of scientists and engineers to pursue careers in astronomy, chemistry, and space exploration. It will fuel public and political support for the next generation of great observatories that can push our capabilities even further. A good mystery is a powerful motivator, and this is one of the greatest scientific mysteries of our time. Its true legacy may not be the answer itself, but the renewed passion for exploration and discovery that it ignites within us all. The universe is vast, and our knowledge is a tiny island in a boundless ocean of the unknown. Each discovery, like this one, does not diminish the ocean of mystery, but in fact reveals its true scale. It shows us how much we still have to learn, how many incredible phenomena are waiting just beyond the edge of our perception. This should not be a daunting thought, but an exhilarating one. It means that the age of exploration is not over, it has barely even begun. The greatest discoveries still lie ahead of us, waiting to be found in the silent darkness between the stars. We are left in a state of profound and wonderful uncertainty. The data is on the table, the hypotheses have been proposed, and the scientific community is now engaged in the slow, careful work of testing them. For now, 3i/Atlas remains an enigma, a beautiful question mark hanging in the cosmic dark. It represents both the limits of our current understanding and the boundless potential for future discovery. It is a symbol of the very frontier of human knowledge, a place where science, philosophy, and a sense of awe converge in the face of the great, silent, and magnificent unknown. The James Webb Space Telescope continues its silent vigil, its golden eye turned outward to other targets, other mysteries. It is currently analyzing the atmospheres of rocky exoplanets, peering back toward the dawn of the first galaxies, and studying the birth of new stars and dusty nebulae. Its mission is far from over, and as it continues to gather light from the farthest reaches of space and time, it holds the potential to deliver the next piece of the puzzle, the next anomalous signal that could once again reshape our understanding of the cosmos and our place within it. The passage of this interstellar object has left an indelible mark on our science and our imagination. It has demonstrated that our solar system is not a closed system, but is open to visitors from other stars. It has provided a chemical signature that defies easy explanation, challenging our models of cometary science. And it has allowed us, however briefly, to entertain one of the most profound ideas ever conceived, that we have detected a relic from another intelligence. The comet is gone, but the questions it has left in its wake will resonate for decades to come. So we continue to look up. We continue to build our instruments, refine our theories, and push our probes farther into the void. We do this because curiosity is encoded in our DNA. The same drive that pushed our ancestors to cross oceans now pushes us to cross the gulfs between worlds. The mystery of 3I/Atlas is not just about a comet. It is about our own unyielding need to understand. It is a chapter in the grand, ongoing story of a sentient species on a small blue planet, slowly awakening to the true scale and wonder of the cosmic ocean in which it resides. The journey through the data of 3I/Atlas leaves us here, on a precipice of possibility. We are balanced between a new and exotic form of natural chemistry and a discovery that would alter the course of history. Science does not yet offer a definitive answer, and so we are left to contemplate the vastness of the universe and the many secrets it still holds. The signal from this distant traveler, whether natural or not, has become a mirror, reflecting our deepest questions, our greatest hopes, and our unending quest for connection in the grand, silent theater of the cosmos. Let us contextualize this potential discovery within the broader human search for cosmic companionship. For over half a century, our primary tool has been the radio telescope, our ears cupped to the heavens, listening for the structured, intelligent whispers of a broadcast. This endeavor, the search for extraterrestrial intelligence, or SETI, has been a patient and often lonely vigil. We have scanned countless star systems across the radio dial, listening for a single, unambiguous signal that would break the great cosmic silence. The work is predicated on the assumption that another civilization would choose this method to communicate, a reasonable but unproven hypothesis about the nature of alien psychologies and technological trajectories. The anomaly of 3I/Atlas represents a profound paradigm shift in this search. It suggests that we should not only be listening, but also looking, and specifically, smelling the cosmos on a chemical level. The search for technosignatures must expand beyond radio waves to encompass the physical and chemical artifacts of a civilization. This is a more patient, more archaeological approach. It does not require a civilization to be actively broadcasting a message to us now. We could detect the ruins of their technology, the faint chemical residue of their industry, or the passive signature of a probe that was launched millions of years before humanity even existed. It transforms the search from a conversation into a forensic investigation. This shift brings us face to face with the Fermi paradox, the profound contradiction between the high probability of extraterrestrial life and the complete lack of evidence for it. The paradox, famously posed by physicist Enrico Fermi, asks, where is everybody? Our galaxy is ancient, with billions of stars older than our sun and billions of planets in the habitable zone. By all statistical logic, the Milky Way should be teeming with civilizations, some of which should have mastered interstellar travel long ago. Yet, we see no great galactic empires, no massive engineering projects, no interstellar superhighways. The sky, to our best instruments, appears silent and natural. This eerie silence is what makes the 3I/Atlas signal so potent and so disruptive. One of the most sobering potential solutions to the Fermi paradox is the concept of the Great Filter. This theory posits that there is some evolutionary or technological hurdle that is so difficult to overcome that it prevents almost all life from reaching a state of interstellar colonization. We do not know where this filter lies in the timeline of life. Perhaps it is the initial spark of life from non-living chemistry. Perhaps it is the jump to complex, multicellular organisms. Or, more ominously, perhaps the filter lies ahead of us, the inevitable self-destruction of intelligent species through nuclear war, environmental collapse, or the misuse of advanced technologies like artificial intelligence. If 3I/Atlas were proven to be an artifact, it would have profound implications for our understanding of this great filter. Its existence would be a beacon of hope, a single data point proving that at least one other species navigated the treacherous path to interstellar capability. It would suggest that the filter is not an insurmountable barrier but a challenge that can be overcome. It would mean that survival is possible. This knowledge would be a tremendous psychological boon for our own species, a confirmation that a long-term future among the stars is not a fantasy, but a real, achievable destiny if we can successfully navigate the challenges that lie ahead of us. Conversely, consider the alternative perspective. A single, ancient, and inert probe could also be interpreted as a more melancholic sign. Why only one? Where are the others? Perhaps we are looking at the sole survivor, the final echo of a civilization that has long since vanished. We might be like archaeologists, discovering a single, exquisitely crafted tool from a lost culture, a testament to their genius but also a confirmation of their ultimate extinction. This probe would then be a beautiful and tragic monument, a warning that even for those who pass the great filter, the universe is a vast and lonely place where even the greatest civilizations can eventually fade into silence. Let us explore the psychological impact of such a confirmation. The initial discovery would likely be met with a mixture of awe, excitement, and a significant degree of fear and trepidation. Our entire worldview, which has been largely anthropocentric for millennia, would be shattered in an instant. The knowledge that we share the universe with older, more advanced intelligences would force a species-wide moment of humility. It would also ignite geopolitical tensions, as nations might vie to control the narrative, the technology, or any future communication. The transition from being the universe's sole intelligence to being its newest members would be the most profound and potentially disruptive social event in human history. The nature of the object itself would dictate much of this reaction. A passive inert probe, as 3I/Atlas appears to be, is perhaps the gentlest possible form of first contact. It is non-threatening, an object of study rather than a direct interlocutor. It allows us time to analyze, to debate, and to come to terms with its existence at our own pace. A direct radio message or the arrival of an active, functioning spacecraft would be a far more immediate and potentially destabilizing scenario. The quiet, archaeological nature of a discovery like this provides a crucial buffer, a chance for humanity to mature into the new cosmic reality it has uncovered. What about the origin of such a probe? Using its trajectory, astronomers can trace its path backwards through the galaxy, but only with a degree of uncertainty that grows larger with time. We could perhaps narrow its origin to a specific sector of the sky, a particular constellation from our perspective on Earth. This would immediately transform that patch of sky into the most scrutinized region of space in history. Every telescope would be turned to the stars along its likely flight path, searching for a home star system that shows other signs of technology, such as an unusual energy signature or a planet with an industrial atmospheric composition. The probe would become a treasure map, guiding our search to a specific celestial shore. We must also consider the vastness of time. If the probe is, for example, 10 million years old, the star system that launched it may look very different today. The parent star itself could have evolved off the main sequence, becoming a red giant or a white dwarf. The planets it once nurtured could be barren, frozen husks. The civilization that sent the probe could be extinct for reasons we could never know. This temporal gulf is one of the most difficult concepts for the human mind to grasp. We may find evidence of our cosmic neighbors but find them only as historical echoes, their light and their relics reaching us long after their story has come to an end. The chemical message itself, the ethylene glycol, will become an object of intense cryptographic and linguistic study. If it were an intentional message, what could it mean? Is the molecule itself, the message, its complex structure, a diagram of some fundamental principle? Or is it a carrier, with information encoded in the isotopic ratios of its constituent atoms? Scientists would search for any deviation from the natural isotopic abundances of carbon, hydrogen, and oxygen, looking for a patterned artificial signal embedded within the very atoms of the gas. This would be a form of communication so advanced and so patient that it makes our own radio broadcasts seem like shouting in the wind. Let us pull back from the speculative and return to the instrument. The James Webb Space Telescope's location at the L2 Lagrange point is a crucial part of its power. This is a gravitationally stable point in space, where the pull of the Sun and the Earth balance perfectly. This allows the telescope to orbit the Sun in lockstep with the Earth, using a minimal amount of fuel for station keeping. More importantly, from this vantage point, the Earth, Moon, and Sun are always in the same direction, allowing Webb to deploy a single, massive sunshield that permanently protects its sensitive optics from their heat and light, enabling the stable, frigid temperatures necessary for its groundbreaking infrared astronomy. The sunshield is an engineering marvel in its own right. A 5-layered, tennis court-sized kite made of a material called capton. Each layer is as thin as a human hair and is coated with aluminum and doped silicon to reflect sunlight back into space. The vacuum between the layers acts as a perfect insulator. The sun-facing side of the shield can reach temperatures hot enough to boil water, while just a few feet away, on the telescope side, the optics are chilled to a deep freeze colder than any natural place on the surface of the Earth. This incredible thermal gradient is the hidden engine behind Webb's power to see the universe's faintest, most distant heat signatures. The discovery of 3IATLAS and its anomaly has already had a significant impact on the planning of future astronomical observations. The scientific committees that allocate Webb's precious observation time are now giving higher priority to proposals for target of opportunity observations of newly discovered interstellar objects. A network of survey telescopes is being optimized to provide earlier warnings of these visitors, giving instruments like Webb more time to schedule and execute detailed follow-up studies. We have learned that these interstellar travelers are not just celestial curiosities. They are high-priority scientific targets that may hold the keys to understanding planetary formation, astrochemistry, and perhaps even our own place in the universe. The data from Webb is also inspiring a new wave of laboratory experiments here on Earth. Astrochemists are now working to replicate the conditions of interstellar space in vacuum chambers, bombarding simulated cometary ices with radiation to see if they can naturally produce ethylene glycol or other complex organics. These experiments are crucial for testing the naturalistic hypotheses. If a plausible pathway for the creation and preservation of this molecule under space-like conditions can be demonstrated in the lab, it would significantly weaken the case for an artificial origin. Science progresses through this constant dialogue between observation, theory, and experimental verification. This single observation validates the entire scientific rationale behind building a large infrared space telescope. Many of the most interesting chemical fingerprints, including those of water, methane, and complex organic molecules, have their strongest spectral lines in the infrared portion of the spectrum. Earth's atmosphere is opaque to most of this light, meaning that these signatures are largely invisible from the ground. Only by placing a telescope in space, far above the obscuring veil of our atmosphere, can we gain access to this rich trove of chemical information. 3I/Atlas is a perfect demonstration of why going to space is not a luxury, but a fundamental necessity for answering our deepest questions. The mystery also highlights the concept of cosmic dispersal, known as panspermia. This is the hypothesis that life itself, or at least its basic building blocks, can be transported between star systems on objects like comets and asteroids. While 3IATLAS shows no direct evidence of life, its existence as an interstellar traveler carrying complex organic molecules proves that the principle of chemical transport is sound. It demonstrates that the chemical ingredients for life that formed in one solar system are not confined there. Over billions of years, the galaxy could be slowly seeded with these prebiotic compounds, making the emergence of life a more probable and widespread cosmic phenomenon. We should also reflect on the previous interstellar visitor that captured our attention, Oumuamua. This object was even stranger than 3I/Atlas. It was highly elongated, tumbling end over end, and it exhibited a slight non-gravitational acceleration away from the Sun without any visible outgassing. This led some prominent scientists to speculate that Oumuamua could have been an artifact, perhaps a solar sail designed to be pushed by starlight. While that claim remains highly controversial, the fact that we have now had 2 interstellar visitors in just a few years, both with profoundly anomalous properties, suggests that the population of objects between the stars may be far more diverse and strange than we ever anticipated. The growing number of these detections is itself a function of our improved technology. We are simply getting better at spotting these faint, fast-moving objects against the background of stars. This implies that for the entire history of our planet, these interstellar messengers have been passing through our solar system, unseen and unnoticed. We are only now in this specific century developing the eyes to see them. It makes one wonder what other subtle phenomena, what other quiet visitors or faint signals are constantly passing us by, still waiting just beyond the threshold of our current technological perception. The universe is speaking, and we are only just beginning to learn its language. Let us consider the implications if the final verdict is a new, natural phenomenon. Imagine it is confirmed that a certain class of comets, formed under specific and rare conditions, naturally produce this complex chemical signature through an internal process. This would be a profound discovery. It would add a new chapter to our understanding of planetary science. It would give us a new tool to probe the conditions of other star systems. A discovery does not need to be aliens to be revolutionary. The expansion of our knowledge of the natural universe is, in itself, one of the most noble and important pursuits of our species. The cosmos is endlessly creative, and discovering a new aspect of its creativity is a victory for science. The narrative of science is one of slowly and patiently replacing our assumptions with evidence. We once assumed the Earth was the center of the universe, that the stars were fixed points of light on a celestial sphere, and that our solar system was the only one. Each of these assumptions fell in the face of new data. The anomaly of 3I/Atlas is now challenging our assumption that cometary chemistry is universally simple. Whether the explanation is a new kind of natural object or something else entirely, our view of the universe will be expanded. This is the guarantee of good science. Even when a specific hypothesis is proven wrong, the process of testing it always leaves us with a deeper and more accurate understanding. The name of the telescope itself is significant. James Webb was the NASA administrator who guided the Apollo program, the effort that first took humanity beyond our own world. His legacy was not just in achieving a single goal, but in building a robust scientific and technological infrastructure that would enable decades of exploration. It is fitting that the telescope bearing his name is now the instrument at the forefront of the search for life elsewhere, extending that initial human journey to the moon into a new, grander journey of the mind and the senses, reaching out to the very edges of the observable universe and into the heart of its most profound mysteries. The data that Webb produces is not a simple image, but a complex, multidimensional dataset that requires immense computational power to process and analyze. The raw data from the telescope is a stream of binary code, which is then passed through a sophisticated software pipeline, calibrated and transformed into scientifically useful formats like spectra and images. This intricate dance between hardware and software, between the telescope in deep space and the data centers on Earth, is a critical and often overlooked part of the discovery process. Every beautiful image and every groundbreaking spectral line is the end product of a long and complex chain of human ingenuity and technological prowess. The professional lives of many young astronomers will now be defined by this mystery. Graduate students will write their doctoral theses on it. Postdoctoral researchers will build their careers attempting to solve it. It will spawn new fields of inquiry, blending chemistry, physics, and geology to understand the nature of these interstellar objects. This is how a scientific field evolves, galvanized by a central, compelling question that focuses the efforts of an entire generation of researchers. The legacy of 3I/Atlas is already being written in the grant proposals, the conference talks, and the research papers of today's scientific community. We must also acknowledge the role of patience in this endeavor. The scientific process is often slow, methodical, and incremental. There may not be a single eureka moment that solves this puzzle overnight. The answer may come years from now, pieced together from dozens of different studies, observations, and experiments. In a world that often demands instant gratification, science offers a different path, one of patient inquiry, of careful consideration of evidence, and of the profound, quiet satisfaction that comes from contributing one small piece to the grand mosaic of human knowledge. The mystery of 3I Atlas will be solved not with speed, but with persistence. The very existence of complex molecules like ethylene glycol, whether naturally formed or not, is a testament to the universe's inherent ability to generate complexity. From the initial simple soup of hydrogen and helium after the Big Bang, generations of stars have lived and died, forging heavier elements in their nuclear furnaces and scattering them into space. These elements then cooled and combined in the dark nurseries of molecular clouds, forming an ever-richer palette of chemical ingredients. Life on Earth is the product of this cosmic chemical evolution. The molecules in 3I Atlas are a part of that same story, a reminder that the universe is not just empty space, but a vibrant, evolving chemical reactor. This brings us to the philosophical concept of cosmic modesty. For centuries, we have placed ourselves at the center of the universe, both physically and metaphysically. Astronomy has been a long, slow process of dethronement, moving us from the center to a small planet orbiting an average star in a typical galaxy. The discovery of even a single alien artifact would be the final step in this process. It would confirm that our intelligence, our technology, and our culture are not unique or special, but are likely just one instance of a common cosmic phenomenon. It would be the ultimate lesson in humility, a powerful and necessary perspective for a young, developing species. It is worth considering how different types of stars might influence the objects that form around them. Our Sun is a relatively stable, yellow G-type star. But what about objects formed around a tiny, cool red dwarf or a massive, intensely hot blue giant? The chemistry and physics of planet and comet formation in those environments would be dramatically different. The intense ultraviolet radiation from a blue giant might catalyze the formation of some complex molecules while destroying others. The low energy of a red dwarf might lead to a different composition of ices. 3I/Atlas is a physical sample from one of these unknown contexts, a geological specimen from an alien star system. One of the most important principles in the search for extraterrestrial life is to avoid being too anthropocentric in our thinking. We tend to look for life as we know it, and technology as we know it. But an alien intelligence that evolved in a completely different environment could have a biology, a psychology, and a technological footprint that are utterly unrecognizable to us. Their probes might not be made of metal and silicon, but of crystalline structures or complex, engineered organic matter. Their communication might not use electromagnetic waves, but something else entirely, like neutrinos or gravitational waves. The anomaly of 3I Atlas is so compelling precisely because it is strange, a hint of a chemistry that falls outside our familiar experience. What if the object is something entirely new, a third category beyond natural object or artificial probe? Some theoretical physicists have postulated the existence of exotic objects made of strange matter or born from cosmic strings. Could 3I Atlas be our first encounter with a type of matter or a physical phenomenon that is predicted by our most advanced theories but has never been observed? In this case, the mysterious gas would not be a sign of alien life, but of alien physics. This would be just as revolutionary, confirming that our understanding of the fundamental constituents of the universe is incomplete, and that the cosmos holds forms of matter far stranger than we have ever imagined. Ultimately, this entire scientific inquiry is a profoundly human story. It is a story about our relentless desire to see what lies over the next horizon. This drive is part of our evolutionary inheritance, a survival trait that pushed us to explore our own planet. Now, with our world fully mapped, we have turned that same innate drive outwards, to the stars. The James Webb Space Telescope is our modern-day caravel, and its discoveries are the new continents of our age. We explore not just for practical gain, but because it is in our very nature to wonder what lies in the dark, and to build a light bright enough to see it. The ongoing analysis of 3I/Atlas is also a race against time in a different sense. Our ability to detect these objects is new, but their passage is not. This means that countless other interstellar visitors have passed through our system in centuries past, their secrets lost to us forever. because we were not yet ready to see them. How many other anomalous objects have we missed? This thought imbues the current search with a sense of urgency. We must make the most of this new observational capability. Because each interstellar object that passes by is a unique and fleeting opportunity to sample the wider galactic environment, an opportunity that will not come again. Let's consider the scale of the journey undertaken by this object. Interstellar space is not entirely empty, but it is an almost perfect vacuum. To travel from a nearby star, even at high speed, would take tens of thousands of years at a minimum. For much of this journey, the object would be in profound darkness, far from the light of any star, at temperatures just a few degrees above absolute zero. It would be bombarded by a steady rain of high-energy cosmic rays. That anything, especially a complex organic molecule, could survive such an arduous journey is a remarkable fact in itself, speaking to the resilience of chemistry and the protective power of being embedded deep within an icy nucleus. The search for technosignatures has often been underfunded and on the fringes of mainstream astronomy. The discovery of a compelling candidate like the 3IATLAS anomaly could change that permanently. It provides a strong, data-driven argument for dedicating more resources and telescope time to this search. It demonstrates that the search for extraterrestrial intelligence is not just a speculative endeavor, but can be a rigorous, observationally driven field of astrophysics. This single detection may do more to legitimize and energize the field than 50 years of patient radio searches, opening up a new and exciting era in our quest for cosmic companionship. A core tenet of science is falsifiability. A hypothesis must be testable, and there must be some conceivable outcome of an experiment or observation that could prove it wrong. The alien probe hypothesis for 3I/Atlas is, in principle, falsifiable. If another interstellar object is found with the same chemical signature, but also with other features that are unambiguously natural, it would refute the idea that this signature is exclusively artificial. Conversely, finding another object with this signature that also exhibits other non-natural properties, like emitting radio waves, would provide powerful confirmation. This testability is what elevates the idea from mere speculation into the realm of legitimate scientific inquiry. The information gathered by Webb is stored in the Mikulski Archive for Space Telescopes, or MAST. This public archive holds the data from dozens of missions, including Hubble, Kepler, and now Webb. It is a treasure trove of cosmic information, available to any scientist, and even the public, anywhere in the world. This open data policy is a cornerstone of modern astronomy. It ensures that the discoveries made by these incredible instruments are not the property of one person or nation, but are a shared resource for all of humanity, allowing for the maximum possible scientific return and ensuring that the data will be reanalyzed for decades to come as our techniques and understanding improve. Think about the future of this search. The next generation of extremely large ground-based telescopes, with mirrors over 30 meters in diameter, will soon come online. While they cannot see in the infrared like Webb, their sheer light-gathering power will allow them to perform incredibly high-resolution spectroscopy on brighter objects. In space, new missions are being designed that will be even more powerful than Webb. The ultimate dream is a mission like the Habitable Worlds Observatory, a telescope designed specifically to find and characterize Earth-like planets around other stars, and to scan their atmospheres for the chemical signs of life. The mystery of 3I/Atlas is a powerful justification for these future investments. The story of 3I/Atlas is a lesson in cosmic perspective. Our lives, our conflicts, and our achievements unfold on a tiny stage in a vast cosmic arena. To contemplate an object that has traveled for millennia between the stars is to be reminded of the immense scales of space and time. It invites us to step back from our immediate concerns and to see ourselves as part of a much grander, more ancient, and more mysterious story. This perspective can be deeply calming and unifying, a reminder that for all our differences, we are all fellow travelers on this one small world, staring out into the same magnificent and enigmatic universe. We must also consider the possibility of error, not a flaw in the telescope, but a subtle misinterpretation of the complex data it produces. The process of converting raw photons into a calibrated spectrum involves many layers of modeling and correction. Is it possible that a subtle, unknown instrumental effect or a flaw in the data processing pipeline could be mimicking the signal of an exotic molecule? Teams of scientists are meticulously reanalyzing every step of this process, a crucial form of internal peer review to ensure that the detection is robust. Before we can claim a revolutionary discovery, we must be absolutely certain that the signal is real and not an artifact of our own tools. The mystery of 3IATLAS has reinvigorated a sense of wonder about our own solar system. If such strange objects are passing through, what other secrets might be hiding in plain sight? Perhaps in the icy bodies of the Kuiper Belt or the distant Oort cloud, there are objects with equally strange and unexpected chemistries, relics from the formation of our own solar system that we have yet to study in detail. This discovery encourages us to look more closely at our own backyard, to explore the remote corners of our own planetary system with the same sense of curiosity and expectation that we apply to interstellar visitors. There are still great discoveries to be made right here at home. Regardless of the final explanation, this event has permanently changed the way we view the cosmos. We can no longer think of the space between the stars as a simple, empty void. We now know it as a dynamic environment, a celestial ocean with its own population of wandering objects, each with a unique story to tell. We have dipped our nets into this ocean for the first time and pulled out something unexpected. This encourages us to keep casting our nets, to continue our surveys, and to build better instruments, because it is now clear that the interstellar sea is far richer and more surprising than we had ever dreamed. The specific choice of ethylene glycol, if it were a message, is intriguing. In the language of chemistry, it is a relatively simple but highly specific molecule. It is not as basic as methane, but not as complex as DNA. It occupies a middle ground that makes it both recognizably artificial and relatively stable. One could imagine a galactic encyclopedia of chemical hellos, where different civilizations choose a different, stable, and unnatural molecule to tag their probes, a way of signing their work. In this grand cosmic art gallery, we would be seeing the signature of a previously unknown artist, a new school of technological thought. The public fascination with this story reveals a deep human yearning for connection, a desire not to be alone in the universe. In a time of global challenges and division, the prospect of a shared cosmic context is a powerful and unifying idea. The thought that there is something more, something grander than our terrestrial affairs, inspires a sense of collective identity as Earthlings. This mystery, therefore, serves a vital social and psychological function. It lifts our gaze from the ground to the sky and reminds us of the shared human enterprise of exploration and the universal quest for meaning in a vast and silent cosmos. Let's re-examine the comet's designation, 3I/Atlas. The 3I signifies that it is the third interstellar object confirmed by science. The Atlas refers to the Asteroid Terrestrial Impact Last Alert System, the survey telescope in Hawaii that first discovered it. This name is a story in itself. An instrument designed to protect us from dangers within our solar system became the discoverer of a profound mystery from far beyond it. It is a beautiful example of how scientific tools often lead to discoveries far outside their intended purpose, and how the search for knowledge in one area can unexpectedly open a door to a completely new and unimagined realm of possibility. If this object is natural, it raises a fascinating question. Could life arise in a planetary system with such an exotic chemistry? If comets are delivering complex antifreezes to nascent planets, could this lead to the formation of subsurface oceans that remain liquid at much colder temperatures? Could it lead to a form of biochemistry that is not based on water, but on a mixture of water and glycol? The discovery could be providing us with the first clues to a completely different pathway for the origin of life, expanding our definition of a habitable world, and opening up vast new real estate in the galactic habitable zone where life might take hold. We are the universe's way of knowing itself. The atoms in our bodies were forged in the hearts of stars billions of years ago. After eons of cosmic evolution, a small part of the universe, humanity, has become conscious and has begun to look back out at its own origins. The James Webb Space Telescope is the latest and most powerful sensory organ that this conscious part of the universe has developed. When it looks at an object like 3I/Atlas, it is, in a very real sense, the cosmos examining itself, trying to piece together its own grand and mysterious story from the faint clues written in ancient light. The solution to this mystery, when it comes, will likely be a moment of profound clarity, where a new piece of evidence or a new insight suddenly makes all the disparate facts click into place. It will be a testament to the power of the scientific method to navigate uncertainty and converge on a coherent explanation. Until that day comes, we inhabit a space of intellectual suspense. We hold multiple competing hypotheses in our minds simultaneously, weighing the evidence for each, without committing fully to any. This state of informed wonder is the true essence of the scientific frontier, a place of immense intellectual excitement and boundless possibility. As we move forward, the story of 3I/Atlas will serve as a crucial benchmark. Future anomalous detections will be compared against it. Has this specific chemical signature been seen again? Do other interstellar objects show different, equally strange anomalies? It has provided a new spectral type for cosmic objects, the ethylene glycol anomaly. Future discoveries will allow us to determine if this type is a singular occurrence, a rare but recurring natural class, or the first of many similar artifacts to be found. The object itself is gone, but its data has become a permanent and vital touchstone in our ongoing cosmic survey. Let us close this chapter of our journey by reflecting on the image of the lone interstellar traveler. For unimaginable lengths of time, it moved through the near-perfect emptiness, a silent witness to the slow dance of galaxies. Its journey is a metaphor for the search for knowledge itself. A long, often solitary voyage through vast unknowns, punctuated by brief, brilliant moments of illumination when we pass near a source of light and truth. The strange gas clouds surrounding 3I/Atlas is one such moment of illumination, a fleeting glimpse of something new that will light our path and guide our questions for many years to come. The final question, then, is not simply what this object was. It is what this object will inspire us to become. Will it inspire us to be more curious, more collaborative, and more daring in our exploration of the universe? Will it encourage us to look at the cosmos not as an empty void, but as a place of infinite possibility and profound mystery? The answers to those questions are not found in the spectral lines of a distant comet, but here, within ourselves. The ultimate legacy of this cosmic messenger depends on how we choose to respond to the incredible and awe-inspiring questions it has placed before us. Behind every great scientific instrument is a multi-generational human story. The James Webb Space Telescope is the culmination of over 20 years of dedicated work from more than 10,000 scientists, engineers, and technicians across the globe. It is a story of immense challenges and breathtaking innovation. They had to invent new technologies, from the specialized materials of the sunshield to the cryogenic actuators that align its mirrors with nanometer precision. For many who worked on it, this mission became their life's work, a singular focus held for decades. The data from 3I/Atlas is not just a scientific result. It is the fulfillment of a long-held human promise, a testament to what our species can achieve when it unites in the pursuit of knowledge. Consider the moment of first light, a critical and anxious time for any new observatory. After its complex month-long unfolding in the vacuum of space, the team had to painstakingly align 18 individual mirror segments, focusing them into a single, perfect point of light. This process, known as wavefront sensing and control, was a delicate and unprecedented remote operation, conducted from a million miles away. The release of the first sharp, focused images was a moment of profound relief and elation, the successful culmination of a quarter-century of effort. It was this perfected vision, this flawlessly engineered eye, that was then turned towards the interstellar visitor, enabling the detection of its faint and mysterious chemical ghost. Let us delve into the nature of scientific evidence itself. In the court of science, a single piece of data, no matter how intriguing, is rarely enough to secure a conviction. The signal from 3I/Atlas is currently best described as a compelling anomaly under investigation. It is not yet proof of anything, natural or artificial. Proof requires a higher standard. It demands repeatability, either by observing the same phenomenon on a new object or by developing a theoretical model that perfectly explains the observation and makes testable predictions. The scientific process is a deliberately slow and skeptical one, designed to protect us from our own innate desire to believe in extraordinary explanations before the evidence is truly overwhelming. One of the most powerful tools in this process is peer review. Before a scientific paper announcing a result like this is published, it is sent to other anonymous experts in the field. These reviewers act as a critical filter, scrutinizing the methodology, checking the calculations, and challenging the interpretations. This rigorous, often demanding process ensures that scientific claims are robust and that potential errors are caught before they become part of the scientific consensus. The analysis of 3I/Atlas is currently undergoing this intense scrutiny, with every aspect of the data and its interpretation being challenged and verified by the global scientific community. This is not a sign of weakness, but the very foundation of scientific strength. The potential for misinterpretation is always present, and history is filled with cautionary tales. In the 1960s, astronomers detected a perfectly regular radio pulse from deep space, and for a brief, exhilarating moment, believed they had found an alien beacon, labeling it LGM-1 for Little Green Men. It was later confirmed to be the first discovery of a pulsar, a new and entirely natural type of spinning neutron star. This story serves as a vital reminder of the scientific maxim: before you claim a discovery of new biology, you must first be absolutely certain that you have not simply discovered new physics or new chemistry. The pulsar was a revolutionary discovery, just not the one originally imagined. Let us expand our view to the concept of a galactic ecology. The Milky Way is not a static collection of stars. It is a dynamic, evolving system. Supernova explosions seed the interstellar medium with heavy elements. The gravitational tides of the galaxy's spiral arms trigger the collapse of molecular clouds, giving birth to new generations of stars and planets. Interstellar objects like 3I/Atlas are the galactic equivalent of pollen or seeds drifting on the cosmic winds. They are a fundamental part of this galactic metabolism, ensuring that the chemical products of one star system are shared with others. This constant exchange enriches the galaxy, increasing the chemical diversity from which new worlds and potentially new life can form. This idea of a connected galaxy forces us to reconsider the origins of life on our own planet. The early Earth was heavily bombarded by comets and asteroids. We now understand that many of these impactors likely originated from the outer solar system, but it is statistically certain that some were interstellar wanderers. These objects could have delivered not just water, but also a rich supply of complex organic molecules, the prebiotic soup of ingredients needed to kickstart life. The very atoms in our bodies, the complex molecules that form our cells, may have cousins that are currently locked in the frozen heart of a comet, traveling through the darkness between the stars. We may be, in a very literal sense, the children of interstellar travelers. The presence of an interstellar object in our system also has implications for our own deep future. As humanity begins to contemplate interstellar travel, we are faced with the immense challenge of shielding a spacecraft and its occupants from the hazards of deep space, primarily cosmic radiation. The fact that a comet like 3I/Atlas can preserve complex, relatively fragile molecules in its interior for millions of years is a valuable lesson. It suggests that a sufficient mantle of ice or rock can provide excellent natural shielding. The study of these objects is therefore not just an abstract science. It provides crucial, practical data that could inform the design of the first generation of human starships. Let's consider the velocity and energy of this encounter. Interstellar objects pass through our solar system at tremendous speeds, typically many kilometers per second. This makes any potential intercept mission incredibly difficult. We cannot simply launch a probe to rendezvous with it as we do with asteroids in our own system. We would have to chase it down on its way out. A successful mission would require a spacecraft with a propulsion system far more advanced than anything we currently possess. The discovery of 3I/Atlas is therefore a powerful technological motivator, highlighting the immense gap between our current capabilities and what is needed to truly engage with these fleeting messengers from other stars. If the probe hypothesis were ever confirmed, it would force us to grapple with a set of profound and difficult questions about contact. should we attempt to respond. A reply sent by radio would take tens of thousands of years to reach the origin star system. Would anyone still be there to receive it? A more immediate action would be to broadcast the discovery to the entire world, and perhaps even send a message into deep space announcing our own existence. Such an act, often called active SETI, is highly controversial. Some argue it is a vital next step, while others warn that we should not advertise our presence until we know more about the nature of the intelligences that may be listening. This brings us to another possible solution to the Fermi paradox, the zoo hypothesis. This idea suggests that advanced civilizations may be common, but that they have chosen not to make direct contact with us, observing us from a distance as we would observe animals in a nature preserve. There might be a galactic policy of non-interference with developing species. In this scenario, a probe like 3IATLAS would not be a message, but perhaps a discrete, passive sensor, a cosmic trail camera sent to gather data on our system. Its anomalous chemical signature could even be an unintentional byproduct, a minor technological leak from a vessel designed to be otherwise perfectly hidden. A related concept is the dark forest hypothesis. This is a more pessimistic take on the Fermi paradox, suggesting that the universe is a dangerous place. In a dark forest, you do not know if other hunters are friendly or hostile, so the safest survival strategy is to remain perfectly silent. Any civilization that reveals its location by broadcasting signals risks immediate annihilation by a more advanced, predatory civilization. In this scenario, the sky is silent not because no one is out there, but because everyone is hiding. A derelict probe drifting through our system would be the equivalent of finding an ancient, spent cartridge on the forest floor, a sign that other hunters have passed this way before. The technology of the James Webb Telescope is what allows us to have this conversation in a data-driven way. Its ability to perform transit spectroscopy, for example, is revolutionary. When an exoplanet passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere. Webb's instruments are so sensitive that they can capture this light and analyze its spectrum, revealing the chemical composition of that alien air. This is how we will search for biosignatures. The same fundamental technique used on 3I Atlas, reading the chemical barcodes in light, is our primary tool for determining which of the billions of exoplanets in our galaxy might harbor life. Imagine what the confirmation of a biosignature on a nearby exoplanet would mean. If Webb were to detect the unmistakable chemical fingerprints of a thriving biosphere, abundant oxygen and methane, for example, it would be a discovery on par with the 3IATLAS anomaly. It would prove that life is not unique to Earth. While it would not confirm intelligent life, it would demonstrate that the galaxy is a living, breathing ecosystem. This would provide a powerful context for the 3IATLAS mystery, making the idea of a technological civilization arising from one of those countless living worlds seem far more plausible. The search for biosignatures and the search for technosignatures are two sides of the same grand scientific quest. Let us return to the comet's core itself. We have discussed its chemistry, but what about its physical structure? Is it a solid, homogeneous body, or is it a loose rubble pile, a collection of smaller ice boulders held together by weak gravity? The way the gas is released could provide clues. A uniform release might suggest a porous interior, allowing the gas to percolate out from a warm core. This internal structure is a relic of its formation process. By studying its physical properties, we can learn about the turbulence, pressures, and temperatures in the protoplanetary disk of its home star system, gaining geological insights into a place we can never visit. The very act of observing this object has a certain cosmic poignancy. For a brief period, the collective attention of one of the universe's intelligent species was focused on this small, inert piece of ice and rock. We projected our hopes, our fears, and our most profound questions onto it. Then, our encounter ended, and it continued its journey, utterly indifferent to the intellectual and emotional turmoil it had caused. The universe does not exist to provide us with answers. It simply is. The meaning we find in it is a reflection of our own consciousness. The story of 3I Atlas is ultimately a story about us, about our capacity for wonder, our passion for inquiry, and our relentless search for meaning in a magnificent, silent cosmos. The potential for future discoveries of this nature is immense. The Vera C. Rubin Observatory in Chile, when it begins its legacy survey of space and time, will be a game-changer. It will photograph the entire visible southern sky every few nights with a 3.2 gigapixel camera. This fire hose of data will allow us to detect and track interstellar objects with unprecedented statistical power. Instead of one or two every few years, we may start discovering them every few months. This will allow us to build up a true census of the interstellar object population, to see if 3I/Atlas is a rare freak or a member of a common, previously unknown class of cosmic wanderers. This future survey capability will also allow for a new strategy: rapid response. Once the Rubin Observatory flags a new interstellar object, its trajectory can be calculated immediately. This information can then be relayed to other telescopes like Webb, which can be retargeted to observe the object while it is still relatively close and bright. This will create a global, coordinated system for studying these visitors. This systematic approach will replace our current, more reactive stance, turning the study of interstellar objects into a mature, predictive field of astronomy, and maximizing the scientific return from each precious and fleeting encounter. Let's consider the composition of Webb's mirror. It is not made of gold for aesthetic reasons, but for pure physics. Gold is exceptionally reflective of infrared light, the very part of the spectrum that Webb is designed to see. It is also a very unreactive element, meaning it will not tarnish or corrode over the telescope's long mission in the harsh environment of space. A thin coating just a few hundred atoms thick is sufficient. The choice of beryllium for the mirror structure is also deliberate. It is both incredibly strong and incredibly lightweight, and it holds its shape at the cryogenic temperatures at which the telescope operates. Every material on Webb is the result of a long chain of deliberate and brilliant engineering choices. The scale of the data Webb generates is staggering. In a single day of observations, the telescope can send back over 50 gigabytes of raw scientific data. Over its mission lifetime, this will amount to a vast archive of cosmic information that will be mined by astronomers for generations. A discovery might be hiding in the data right now, waiting for the right person with the right algorithm to uncover it. The answer to the 3IATLAS mystery might even come from a reanalysis of the original data years from now, when our understanding of the telescope's instruments has improved. Or when a new chemical theory provides a framework that makes the strange signal suddenly snap into perfect, natural sense. What if the object was designed to be found? This is the essence of a Bracewell probe. The concept, proposed by physicist Ronald Bracewell, is that a long-lived autonomous robotic probe is a far more efficient way to search for other intelligences than sending radio signals. The probe can travel to a star system, enter a stable orbit, and then wait, perhaps for millennia, until it detects the emergence of a technological civilization. Once it detects our radio signals or the industrial pollutants in our atmosphere, it could then activate a beacon to initiate contact. Is it possible 3I/Atlas is such a probe, and its chemical signature is not a leak, but a deliberate, passive signal, the equivalent of a knock on the door? This deepens the mystery of its trajectory. A Bracewell probe would likely be designed to enter a stable parking orbit around our Sun, not to fly through the system at high speed and then leave again. The object's hyperbolic, unbound trajectory argues against it being a probe that is currently active and trying to make contact. However, it could be a defunct probe. Or it could be a flyby probe, designed only to gather data as it passes through, its mission being to survey as many star systems as possible over millions of years. Or perhaps we have misunderstood its capabilities, and its high speed is a sign of a propulsion technology we cannot comprehend. Each possibility opens a new and fascinating avenue of speculation. The James Webb Telescope observes a universe that is fundamentally historical. Because of the finite speed of light, we see everything in the past. We see the Andromeda Galaxy not as it is today, but as it was 2.5 million years ago. We see the most distant galaxies as they were over 13 billion years ago, when the universe was in its infancy. This light travel time is a crucial concept. It means that astronomy is a form of time travel. When we look at 3I/Atlas, we are seeing the gas that was released from it hours before. When we speculate about its origin, we are contemplating a star system whose light may take 100,000 years to reach us. We are always looking at echoes of the past. The existence of this puzzle has a unifying effect on the human spirit. In a world often fractured by political and cultural divides, the search for our place in the cosmos is a shared endeavor that transcends national borders. The James Webb Space Telescope itself is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. The data it produces is shared globally. When we contemplate the possibility of life elsewhere, we are forced to see ourselves not as members of different tribes, but as representatives of a single entity, planet Earth. This cosmic perspective is one of the most valuable and often overlooked gifts that the science of astronomy gives to humanity. Let us contemplate the silence. Even if 3I/Atlas is a natural object, the lack of any other confirmed technosignatures remains a profound and defining feature of our universe. The silence could be a message in itself. It could be telling us that the emergence of technological intelligence is an extraordinarily rare event, that what has happened here on Earth may be one of the most precious and improbable occurrences in the history of our galaxy. This would not be a lonely thought, but a deeply empowering one. It would place a profound responsibility upon our shoulders to cherish, to protect, and to ensure the long-term survival of the only known outpost of consciousness in this vast cosmic ocean. We can also re-examine the object's thermal properties. Webb's instruments can measure the temperature of the nucleus and the gas cloud with great precision. This data can help distinguish between different heating mechanisms. If the gas is significantly warmer than it should be from solar heating alone, it would be strong evidence for an internal energy source, such as radioactive decay or a technological power plant. The thermal data gathered so far has been complex and difficult to interpret, but a more detailed analysis of the comet's heat signature is one of the most promising avenues for distinguishing between the competing hypotheses and adding another crucial piece to this intricate cosmic puzzle. The chemicals detected around 3I/Atlas are part of a larger cosmic story of organic chemistry. Using radio telescopes, astronomers have detected over 200 different types of molecules in the cold, dark clouds between the stars. These range from simple molecules like water and carbon monoxide to complex organic compounds with long carbon chains, and even ringed molecules like benzene. It seems the universe is a natural factory for producing the building blocks of life. The question is no longer whether organic chemistry is common in the cosmos, but how these prebiotic ingredients are assembled into the first self-replicating living systems. The interstellar medium is a sea of possibility, and objects like 3I/Atlas are the vessels that carry its cargo between the stars. This discovery also has a subtle influence on our art and culture. Science fiction has long explored the idea of first contact, but it has often been imagined as a dramatic, unambiguous event. The reality of the 3I/Atlas situation is more nuanced, more mysterious, and perhaps more realistic. It is a slow-burn detective story, played out in the faint signals of a spectrometer. This will undoubtedly inspire a new generation of stories that explore this more subtle and scientific form of encounter. Art and science have always had a symbiotic relationship, each inspiring the other to look at the universe in new ways. This mystery is a powerful new muse for our collective imagination. The final analysis of this object will likely involve a Bayesian approach. This is a statistical method that allows scientists to update their beliefs about a hypothesis as new evidence comes in. You start with a prior belief, for example, a very low probability for the alien hypothesis. Then, as each new piece of data comes in, you use it to update that probability. If a piece of evidence is hard to explain with natural theories but is consistent with the artificial theory, the probability for the alien hypothesis goes up slightly. It is a rigorous, mathematical way of weighing evidence and is perfectly suited for a complex problem like this, where the final answer may be one of probability, not absolute certainty. The search for knowledge is an infinite game. Unlike a finite game, which is played for the purpose of winning, an infinite game is played for the purpose of continuing the play. Science is an infinite game. The goal is not to find a final answer to everything, but to refine our understanding, to ask better questions, and to keep the process of discovery going. The mystery of 3I/Atlas is a beautiful move in this game. It does not end the conversation, it enriches it, opening up new lines of inquiry and ensuring that the grand, noble game of scientific exploration will continue for generations to come, played out on the magnificent board of the cosmos itself. Let us return our gaze to our own small world, the only data point for life we have. Every living thing on Earth, from the smallest bacterium to the largest whale, shares the same fundamental biochemistry and the same genetic code. This suggests a single origin, a last universal common ancestor from which all terrestrial life is descended. This makes Earth a potentially biased sample. It is possible that life could arise from a completely different set of chemical principles, a second genesis that we have not yet discovered. The exotic chemistry hinted at by 3I/Atlas is a tantalizing clue that the universe might be more biochemically creative than the single example on our own planet would suggest. The pursuit of answers to these grand questions is not a luxury. It is a vital part of what makes us human. It fuels our innovation, driving technological progress that has benefits across all of society. The technologies developed for the James Webb Telescope, for instance, have applications in fields as diverse as medical imaging and laser eye surgery. More importantly, this quest gives us a sense of shared purpose and perspective. In a world beset by short-term problems, the long-term, multi-generational endeavor of cosmic exploration is a powerful source of hope and inspiration. A reminder of the incredible things we can achieve when we look beyond ourselves and work together. It is also possible that the chemical signature of 3I Atlas is not from the object itself, but from something that happened to it. Could the comet have passed through the debris field of some ancient alien technological event? For example, the wreckage of a battle, the remains of a self-destructed probe, or the remnants of a massive astroengineering project. In this case, the comet would be an innocent bystander that collected this anomalous material on its surface. It would be a secondary piece of evidence, a cosmic dust cloth that wiped a surface we cannot see and brought a sample of it back to us. This would make the mystery even deeper, hinting at a galactic history of which we have no knowledge. The scientific journey is often a meandering path, not a straight line. An investigation begins with one question and often ends by answering a completely different one. We began by asking about the composition of an interstellar comet. We may end up discovering a new law of chemistry, a new process of planet formation, or something even more profound. This is the beauty of curiosity-driven research. It cannot be planned or predicted. We follow the evidence where it leads, and, in doing so, we often stumble upon discoveries far more significant than the ones we were originally looking for. The true destination of this intellectual voyage is still unknown. The light collected by the James Webb Telescope from this faint comet is incredibly scarce. We are literally counting individual photons, the fundamental particles of light. The spectral signature is built up over many hours of observation. As each photon is captured, its energy measured, and its contribution added to the growing dataset. It is an act of cosmic patience, accumulating these tiny messengers of light to build a coherent picture of a distant reality. Every single photon that traveled for years from that object to land on Webb's mirror is a precious piece of the puzzle, a whisper from the void that our technology has finally allowed us to hear. The enigma of 3I Atlas underscores the importance of preserving our own planet as an astronomical observatory. The increasing number of satellite constellations in low Earth orbit threatens to fill the night sky with streaks of reflected sunlight, potentially contaminating the sensitive observations of ground-based telescopes. Light pollution from our cities has already erased the Milky Way from view for a majority of the world's population. To continue our exploration of the cosmos, we must be mindful stewards of our own skies, ensuring that future generations will still be able to look up and wonder, and that our scientific instruments can continue their vital work with a clear, untarnished view of the universe. A civilization capable of launching interstellar probes would likely be a Type 1 civilization on the Kardashev scale, or perhaps even higher. This scale categorizes civilizations based on their energy consumption. A Type 1 civilization can harness all the energy of its home planet. A Type 2 can harness all the energy of its host star, perhaps using a structure like a Dyson sphere. A Type 3 can harness the energy of an entire galaxy. We are currently a Type 0 civilization, still primarily using the fossilized remains of ancient life for our energy. The existence of an interstellar probe would be evidence of a civilization far more advanced and powerful than our own, a humbling and awe-inspiring thought. Consider the information density of this potential discovery. A single spectral line, if proven to be artificial, would contain more profound information than all the books in all the libraries on Earth combined. It would answer one of the deepest questions of human existence and open up 1,000 new ones. It is a perfect example of the elegance and power of scientific measurement. Sometimes the most significant truths are not written in long, complex treatises, but are encoded in the simplest and most fundamental physical properties of the universe, waiting for an instrument sensitive enough to detect them and a mind curious enough to understand their meaning. We must also consider the possibility that we will never know the true answer for certain. The object is gone, and unless we find another one just like it, we may be left with only this single, tantalizing dataset. Science does not always provide neat, tidy conclusions. Sometimes it leaves us with enduring mysteries, questions that are passed down from one generation of scientists to the next. And perhaps there is a certain beauty in that. A universe with all its mysteries solved would be a far less interesting place. This puzzle may become one of the great unresolved questions of our time, a permanent fixture in our cosmic imagination that perpetually inspires us to keep searching. The story of 3IATLAS has unfolded during a unique time in human history, when our ability to observe the universe has taken a quantum leap forward, but our ability to travel within it remains limited. We are in a transitional phase, like a child who has just been given a powerful telescope and can see the distant mountains for the first time, but does not yet have the means to journey to them. This creates a powerful tension, a yearning to bridge the gap between seeing and visiting. This tension is a powerful driver of innovation, and it will be the primary force that pushes humanity from being a planetary species to, one day, becoming an interstellar one. Let's synthesize the journey we have been on. We began with a new eye on the cosmos, the James Webb Space Telescope, a triumph of human ingenuity. This eye was turned to a fleeting visitor from another star, a small, dark comet named 3I/Atlas. It detected a chemical signature, an unexpected abundance of ethylene glycol that challenges our fundamental understanding of cometary science. This single, anomalous data point has forced us to explore the frontiers of our knowledge, considering everything from exotic natural chemistries and internal radioactive heating to the profound and history-altering possibility that we have found the first evidence of technology from beyond our solar system. We have weighed the competing hypotheses, not to find a premature answer, but to appreciate the process of scientific inquiry itself. We have seen how science operates at its best, with a careful balance of open-minded speculation and rigorous, evidence-based skepticism. The mystery has pushed us to consider the grandest questions: the Fermi paradox, the nature of life, and our own place within the vast timeline of cosmic history. It has become a focal point for our hopes, our fears, and our deepest philosophical ponderings. The comet has acted as a catalyst, transforming a simple astronomical observation into a deep and multifaceted exploration of the human condition. The final verdict on 3IATLAS remains unwritten, held in a delicate state of scientific suspense. It could be the first example of a new class of natural object, a discovery that will rewrite our textbooks on planet formation. Or it could be the long-sought signal that confirms we are not alone, a discovery that will rewrite our understanding of everything. Both possibilities are profound. Both outcomes represent a significant leap forward in the human quest for knowledge. The uncertainty is not a sign of failure, but a hallmark of being on the absolute cutting edge of exploration, where the map is blank and any direction could lead to a new world. Regardless of the outcome, the awe and wonder inspired by this mystery are a vital part of the experience. To contemplate the vast, silent journey of this object, to appreciate the incredible technology that allowed us to see it, and to grapple with the immense implications of what it might be, is to engage with the universe on a deeper, more meaningful level. This sense of awe is a powerful antidote to the mundane, a source of perspective that can be both humbling and exhilarating. It connects us to the grand, unfolding story of the cosmos and reminds us that we are privileged to live in an age of unprecedented discovery. This is the essence of cosmic exploration. It is a journey outward that is simultaneously a journey inward. As we probe the secrets of the universe, we learn more about our own capabilities, our own limitations, and our own deepest desires. The faint light from a distant comet becomes a mirror, reflecting our own intelligence, our own curiosity, and our own unyielding search for meaning. The story of 3I/Atlas is therefore not just a story about a comet. It is a story about the sentient universe looking back at itself, filled with a profound and contemplative sense of wonder. The silence of space is not empty. It is full of potential. It contains all the discoveries we have not yet made, all the questions we have not yet thought to ask. The 3IATLAS anomaly is a single note plucked from this immense silence, a brief sound that has resonated through the halls of science and the corridors of our imagination. It has reminded us that the universe is not a static, predictable machine, but a place of endless surprise and profound mystery. And it has assured us that as long as we continue to listen with our instruments and our minds, the silence will, from time to time, break and share with us another one of its extraordinary secrets. We are left with a feeling of profound connection. We are connected to the past, to the generations of scientists who built the foundations upon which we now stand. We are connected to the future, to the generations who will inherit our data and continue this search. And we are connected to the cosmos itself, made of the same star stuff as the object of our study, bound by the same physical laws, and participants in the same grand evolutionary story. This sense of universal connection is the ultimate gift of astronomy, a quiet, contemplative peace that comes from understanding our true context in the magnificent scale of reality. As we conclude this deep analysis, let the sense of mystery settle. Allow the uncertainty to be a space for contemplation. The universe has presented us with a beautiful and elegant puzzle. The pieces are on the table, and the brilliant minds of our time are carefully working to fit them together. We are privileged to be witnesses to this process, to watch the story unfold in real time. The final picture is not yet clear, and that is what makes this moment so precious and so exciting. We are standing at the edge of a great intellectual vista, peering into the unknown, filled with a calm and profound sense of anticipation for the discoveries that are yet to come. The night sky has been a source of wonder and inspiration for every human culture throughout history. We have looked up to navigate our world, to mark the passage of time, and to find our place in the grand scheme of things. Today we continue that ancient tradition, but with new eyes, capable of seeing farther and deeper than our ancestors could ever have dreamed. The James Webb Space Telescope is the modern heir to that timeless human legacy of stargazing. The mystery of 3I/Atlas is the latest verse in the epic poem that we have been writing about our relationship with the cosmos since the dawn of our consciousness. In the end, the journey into the heart of this cosmic mystery leaves us in a state of contemplative awe. We have been confronted with the limits of our knowledge, but also with the incredible power of our scientific methods. We have considered possibilities that stretch the very boundaries of our imagination. And we have been reminded that we live in a universe that is not only stranger than we imagine, but stranger than we can imagine. The strange gas cloud of 3I/Atlas, whether a natural marvel or an alien echo, has served its ultimate purpose. It has made us look up. It has made us think. And it has filled us with a profound and enduring sense of wonder. Ultimately, this interstellar object has become a cosmic mirror. In its enigmatic reflection, we see not a definitive answer, but a perfect image of our own scientific and philosophical boundaries. The questions we ask of it: is it natural? Is it artificial? Is it a message? Are projections of our own hopes, our own anxieties, and our own profound desire to find context in a seemingly infinite universe. We scrutinize its chemical composition, but in doing so, we are truly scrutinizing the composition of our own worldview. Its ambiguity forces us to confront the limits of our knowledge, which is the first and most crucial step toward expanding them. The mirror shows us not what is, but what we are ready to question. This cosmic mirror also reflects our own first tentative steps into the interstellar ocean. For decades, our Voyager probes have been traveling outwards, now beyond the heliopause, carrying their golden records, a message in a bottle from humanity. They are our silent emissaries, our own technological fossils in the making. 3I/Atlas, if it is an artifact, would be the inverse of our Voyager probes, not our message going out, but another's message coming in. It forces us to imagine the civilization that might one day find our silent probe, and to contemplate what they might think of us. It connects our own nascent interstellar ambitions to a potentially ancient and vast galactic heritage of exploration. We must acknowledge the profound loneliness of our own probes. They drift in silence, their power sources slowly decaying, their chances of ever being found infinitesimally small. The potential discovery of an interstellar probe in our own system is a stark reminder that we might be on the receiving end of a similar, ancient story. The intelligence that launched it might have felt the same hope and the same sense of profound isolation that we did when we launched Voyager. The object, whether natural or artificial, becomes a point of empathy, a way to connect with the shared experience of existence in a universe where the distances are vast and the chances for connection are fleeting and precious. Any sufficiently advanced technology is indistinguishable from magic, a famous maxim states. Perhaps a more accurate version for astrophysics would be that any sufficiently advanced technology is indistinguishable from a natural anomaly. We search for signals and structures that make sense to our technological paradigm, but a civilization a million years older might operate on principles of physics we have not yet discovered. Their technology might be biological, or it might manipulate space-time in ways that appear to us as strange gravitational effects or unusual chemical signatures. The 3IATLAS anomaly may be so compelling precisely because it is not an obvious radio signal, but something far more subtle, a potential technosignature so advanced that it sits on the blurry line between chemistry and intention. This brings us to a deeper meditation on the nature of scientific truth. It is not a sudden revelation, but a slow, emergent property of meticulous observation, rigorous debate, and the gradual accumulation of evidence. A discovery like this is not a single event, but a process. It unfolds over years, through countless hours of analysis and peer review. The truth about 3IATLAS will not be decided by public opinion or a single definitive paper, but will crystallize slowly as more data is gathered and as our theoretical understanding matures. This patient, deliberate process is the greatest strength of science, ensuring that its conclusions are built on a foundation of unshakable, verifiable evidence, however long that foundation takes to construct. In this patient process, skepticism is the most valuable tool. Not the cynicism that dismisses new ideas, but the rigorous, intellectual skepticism that demands extraordinary evidence for extraordinary claims. Every scientist working on this problem is acting as both a proponent of their own hypothesis and as its most severe critic. They are actively trying to disprove their own ideas, to find the flaw in their own logic. This internal crucible of doubt is what purifies scientific inquiry. The possibility that 3I/Atlas is an artifact will only be taken seriously by the scientific community if it is the only hypothesis left standing after this exhaustive, skeptical process has failed to find any other plausible explanation. The story of 3IATLAS will now be permanently enshrined in the archives of science, its spectral data a new touchstone for future inquiry. For decades to come, astronomers will download this dataset and reanalyze it with new techniques and new theoretical models. It will be cited in thousands of papers, a foundational data point in the emerging field of interstellar archaeology. The object itself may be gone, but its informational ghost will haunt our libraries and our laboratories, a persistent and productive mystery that will continue to inspire and challenge us. This is the immortality of scientific data, its ability to speak to future generations and to continue yielding new insights long after the moment of its collection has passed. Let us appreciate the profoundly collaborative nature of this quest. There is no single hero in this story. The discovery was made by an automated survey telescope. The crucial data was gathered by an international space observatory. The analysis is being performed by a decentralized global community of scientists, communicating and debating across borders. This is a model for how humanity can solve its most complex problems. By pooling our intellectual resources, by sharing our data openly, and by engaging in a culture of constructive, critical debate, we can achieve a level of understanding that would be impossible for any single individual or nation to reach alone. The mystery has brought out the best in our collective scientific spirit. We now zoom our perspective out to the scale of our home galaxy, the Milky Way. It is a vast, spiral city of stars, containing perhaps 400 billion suns. Statistical estimates based on data from telescopes like Kepler suggest that there may be over 50 billion Earth-like planets in our galaxy alone. 50 billion potential cradles for life. As we gaze upon the majestic sweep of the galactic disk, we are looking at an arena of unimaginable potential. The laws of physics and chemistry are the same everywhere. If life could arise here, under the light of our mediocre yellow sun, it seems almost inevitable that it has arisen countless times elsewhere in that shimmering river of stars. This idea is formalized in the Copernican principle, the foundational assumption that there is nothing special or privileged about our planet or our position in the universe. We are not the center of the cosmos. We are a typical planet orbiting a typical star in a typical galaxy. If we accept this principle, then our existence implies the existence of others. The silence we perceive in the universe becomes an even deeper and more profound puzzle. The anomaly of 3I/Atlas, therefore, does not arrive in a vacuum. It arrives in a context where our best science predicts that such signs of other intelligences should exist. It is a single, tantalizing piece of data that aligns with our most fundamental statistical expectations about the cosmos. We must also embrace the concept of deep time. Our galaxy is over 13 billion years old. Our solar system is a relative newcomer, at only 4.5 billion years old. Intelligent life could have arisen on a planet orbiting an older star billions of years before Earth was even formed. Civilizations could have risen, expanded across the galaxy, and vanished into extinction, leaving behind only faint ruins and silent artifacts, long before the first microbes stirred in the oceans of our world. We may be latecomers to a very old and storied galactic stage. Our search for life is not just a search for our contemporaries, but a form of archaeology on a cosmic scale, sifting through the ruins of immense and ancient histories. From this perspective, the Milky Way can be seen as a single superorganism evolving over cosmic timescales. Stars are born from interstellar gas, they create heavy elements, and then they die, returning those elements to the galaxy to form the next generation. It is a closed, recycling ecosystem. Life, if it is common, would be a fundamental part of this galactic life cycle. The anomaly of 3I/Atlas, whether natural or artificial, is a physical manifestation of this cycle. It is a piece of another star system's history that has been ejected and has now intersected with our own. It is a tangible link, a physical thread connecting our small solar system to the grand, interconnected, and evolving story of the entire galaxy. The enduring legacy of this encounter will be one of profound motivation. The mere possibility that 3I/Atlas is an artifact will galvanize our efforts to explore the cosmos for a century to come. It will provide a powerful justification for building the next generation of space telescopes, instruments even more powerful than Webb, designed specifically to hunt for technosignatures and biosignatures. It will inspire engineers to develop the advanced propulsion systems needed to one day intercept one of these interstellar visitors. This single, ambiguous signal has done more to energize the search for extraterrestrial intelligence than any previous event, transforming it from a passive search into an active, ambitious program of exploration. This mystery has permanently expanded our toolkit. The search for technosignatures is no longer just about radio signals. We now know to look for chemical anomalies, for industrial pollutants in exoplanet atmospheres, for strange thermal signatures, and for physical objects that do not conform to our understanding of natural physics. The parameter space of our search has grown exponentially. 3IATLAS has taught us to think more creatively, to be more like forensic chemists and less like passive listeners. This broader, more inclusive definition of what constitutes a signal will dramatically increase our chances of one day finding the unambiguous evidence we seek. Culturally, this story has brought a deeply abstract and philosophical question into the tangible present. Are we alone? Is no longer a question reserved for late-night conversations. It is a question being actively investigated with our most advanced scientific instruments. It has demonstrated that this is a question that science can, and will, eventually answer. This shift in public perception is crucial. It fosters a deeper appreciation for the scientific process and a greater sense of connection to our shared cosmic environment. It has reminded millions of people to look up at the night sky, not as a static backdrop, but as a dynamic frontier of active and profound discovery. What 3IATLAS leaves us with, more than anything else, is a renewed and powerful sense of possibility. It has cracked the door open to a universe that is potentially far more interesting, more complex, and more populated than we have ever had direct evidence for before. It allows us to dream, but to dream with the rigor of scientific data as our guide. It is a validation of our cosmic optimism, the deeply held human hope that we are part of something larger. This sense of possibility is an intangible but incredibly valuable scientific result. It is the fuel that will power our curiosity and drive our exploration for the long journey ahead as we continue to seek our true place among the stars. And so, our voyage through this deep mystery brings us back to a quiet and contemplative space. We are left not with a simple answer, but with a richer, more profound appreciation for the questions. We are invited to step outside on a clear night, to look up at the silent, star-dusted darkness, and to see it with new eyes. That sky is not empty. It is a library of cosmic history, filled with the light of ancient suns and the echoes of distant events. It is an ocean of possibility, through which silent travelers like 3IATLAS are constantly moving, each carrying a secret from its unknown home. Consider the photons that the James Webb Telescope collected, tiny, individual packets of light that traveled for years, perhaps centuries, across the immense and empty gulf of space. They crossed the solar system, dodged dust particles and planetary magnetic fields, and finally, by a miracle of engineering, landed on a gold-plated mirror a million miles from Earth. In that moment of contact, a journey ended and a new one began. The information carried by those photons began a new voyage through our computers, our scientific papers, and our minds, igniting a conversation that has rippled across our entire planet. It is a profound illustration of how even the smallest and faintest of signals can change the world. Let us embrace the beauty of the uncertainty. To know everything would be to end the journey. The fact that the universe can still present us with a puzzle so fundamental, so elegant, and so perfectly balanced between the known and the unknown is a gift. It tells us that we are still in the heroic age of exploration. It assures us that there are still great discoveries to be made, great mysteries to be solved. The silence of space is not a void. It is a canvas. It is upon this grand, dark canvas that we paint our theories, our hopes, and our ongoing collective search for understanding. The mystery of 3IATLAS is simply the latest, most beautiful brushstroke. This entire inquiry ultimately leads to a state of profound awe. It is the feeling of standing before something immense, something ancient, and something far greater than oneself. It is the humility that comes from recognizing the vastness of our ignorance in the face of the universe's complexity. But this is not a fearful or diminishing feeling. It is an expansive and deeply peaceful one. It is the feeling of connection to the grand cosmic drama, the recognition that we are a small but significant part of a magnificent and unfolding story. This awe is the true reward of scientific inquiry, the emotional and philosophical payoff for our relentless curiosity. From this state of awe, we can find a new perspective on our own world. The Earth, seen from the vantage point of this cosmic mystery, is revealed in its true context. A single, fragile, and incredibly precious oasis of life in a vast and silent desert. The possibility of another intelligence does not diminish our own significance. It enhances it by framing it as a rare and wonderful phenomenon. The challenges we face on this planet, our divisions and our conflicts, appear smaller and more manageable when viewed against the backdrop of interstellar distances and cosmic timescales. The search for life elsewhere is also a search for wisdom here at home. We have been on a journey of scale, from the nanometer precision of a telescope's mirror to the billion light-year sweep of the cosmos. We have traveled from the concrete certainty of a spectral line to the most abstract heights of philosophical speculation. This ability to shift our perspective, to hold the infinitesimal and the infinite in our minds at the same time, is one of the unique capabilities of human consciousness. It is this mental flexibility that allows us to be scientists, to build the tools and the theories that can bridge the immense gap between our small world and the vast universe it inhabits. Let us imagine the future, a time when this question is answered. If 3I/Atlas is found to be natural, our knowledge of the universe will be richer, our models of planetary science more complete. we will have added a new and wonderful creature to our cosmic bestiary. If it is found to be artificial, human history will be forever divided into two eras: the time when we thought we were alone and the time after. In either case, we will be wiser. There is no outcome in which this discovery does not represent a monumental step forward for our species. The pursuit of this question is, in itself, a guaranteed victory for knowledge. The story of 3I/Atlas is a testament to the power of looking. For most of our history, the universe was a place of myth and superstition. We could only guess at its nature. But with the invention of the telescope, we began a new relationship with the cosmos, one based on observation and evidence. We replaced guesswork with measurement. The James Webb Space Telescope is the current apex of that centuries-long journey. It is a pure instrument of seeing, and it has shown us that even after 400 years of telescopic observation, the universe still retains its capacity to startle, to perplex, and to fill us with a profound and transformative sense of wonder. Let the final feeling be one of peace. The universe is not chaotic or malevolent. It is a place of sublime order, governed by elegant physical laws that we are slowly, patiently uncovering. It is a place of immense beauty, from the delicate tendrils of a nebula to the majestic sweep of a spiral galaxy. And it is a place of profound possibility. The mystery of 3I/Atlas does not disturb this cosmic peace, it enhances it. It adds a new layer of potential, a new and fascinating texture to the grand, silent, and magnificent tapestry of reality that surrounds us on all sides. We began this journey with a question posed by a faint gleam of light from the darkness. We ended with a deeper understanding, not yet of the answer, but of the immense and beautiful scope of the question itself. We have learned that our universe is a place where interstellar travel is a reality, where complex organic chemistry is abundant, and where the line between natural anomaly and artificial design can be beautifully and tantalizingly thin. We have been reminded that the greatest adventures are not just physical journeys to other worlds, but intellectual journeys into the heart of a great mystery. As the James Webb continues its mission, it carries our collective curiosity with it. It is our proxy, our silent sensory organ exploring the realms we cannot yet reach. Each photon it collects is a part of our shared human endeavor to understand. The telescope will continue to find new exoplanets, to witness the birth of new stars, and to peer back to the dawn of time. And it will continue to watch for other visitors from the interstellar darkness. The story of 3I/Atlas is not an end, but a beginning. It is the prologue to a new and exciting chapter in our cosmic story, a chapter we are all privileged to be living through right now. The search for knowledge is a form of communion with the universe. It is an act of deep listening, of paying close and careful attention to the subtle clues the cosmos provides. In this quiet, focused attention, we can sometimes glimpse the underlying elegance and interconnectedness of all things. The mystery of 3I/Atlas has provided us with a perfect opportunity for this kind of cosmic communion. It has quieted our own noise and has forced us to listen, with all our technological and intellectual might, to a faint and enigmatic whisper from the vast silence between the stars. Let this story serve as a reminder of the value of the unknown. In a world that often prizes certainty, it is the mysteries, the open questions, and the uncharted territories that truly drive us forward. The unknown is not a void to be feared. It is a landscape of possibility to be explored. 3I/Atlas has gifted us a vast and beautiful new wilderness for our scientific imagination. The exploration of this new territory, with all its challenges and its potential rewards, will occupy us for many years to come, and it will leave us richer and wiser for having made the journey. This interstellar visitor, in its brief passage through our lives, has acted as a profound cosmic teacher. It has taught us about chemistry, about physics, and about the process of science. But its greatest lesson has been more philosophical. It has taught us humility in the face of the unknown, patience in the search for truth, and a renewed sense of awe for the magnificent and deeply mysterious universe that is our home. The knowledge it has imparted is not just a collection of facts, but a deeper and more contemplative state of mind, a way of seeing our world and ourselves in a new cosmic light. We are a species of storytellers, and this is now one of our great stories. It is a detective story written on a cosmic scale, a tale of a mysterious visitor and a brilliant detective in the form of a golden telescope. It is a story that has all the elements of our most enduring myths, a journey into the unknown, a confrontation with a profound mystery, and a quest for a truth that could change the world. This narrative is now part of our culture, a new piece of our collective understanding of the universe, and it will be told and retold, inspiring future generations to continue the grand and unending human quest for knowledge. As we move forward from this exploration, let us carry with us the sense of perspective it has offered. The everyday concerns of our lives are real and important, but they exist within a far grander context. We are inhabitants of a small planet, blessed with a brief moment of consciousness, adrift in a universe of staggering scale and beauty. To remember this context is to find a source of enduring calm and quiet strength. It is to understand that we are part of a story that is far older, far larger, and far more mysterious than our own, and that there is a profound peace to be found in that understanding. The light from 3IATLAS has now passed us by, continuing its journey out into the wider cosmos. But the light of understanding that it has ignited within our minds remains. This is the beautiful asymmetry of scientific discovery. The universe provides a fleeting stimulus, a transient signal, and in return, a permanent change is created within our collective consciousness. A new idea is born, a new field of inquiry is opened, and our map of reality is redrawn, forever expanded and enriched by the brief encounter. The object is gone, but its impact on us is a permanent and positive transformation. Let us appreciate the elegance of this mystery. It is not a noisy, chaotic event, but a quiet, subtle one. The evidence is found not in a dramatic explosion, but in the faint, dark absorption lines of a spectrum. This subtlety is a reflection of the universe itself. The most profound truths are often not the loudest ones. They are the quiet patterns, the subtle harmonies, and the elegant laws that govern the silent dance of planets, stars, and galaxies. The story of 3IATLAS has taught us to listen more closely to the universe's quietest whispers, for it is often in these that the most important secrets are told. We stand today in a unique moment of cosmic history. We are the first generation of human beings to possess the technology to meaningfully search for the chemical signs of life and intelligence beyond our own world. We are the pioneers of this new form of exploration. Future generations will look back on this time, the era of Hubble and Webb, as a golden age of discovery, a time when the universe began to open up to us in ways that were previously unimaginable. We are living in the very moment that our descendants will read about in their history books, and the mystery of 3I/Atlas will be one of its most important and compelling chapters. The search for answers continues. Even now, as you watch this, scientists are at their desks, running new simulations, debating new theories, and drafting new proposals for telescope time. The intellectual energy ignited by this anomaly is immense and continues to grow. This is the heartbeat of science, a restless, unyielding, and passionate drive to understand. The story is not over. It is unfolding day by day in the quiet, diligent work of thousands of curious minds around the world, all focused on that one faint signal from the dark. The final answer is not yet known, but the process of finding it is a beautiful and inspiring thing to witness. We are, in a sense, the memory of the universe. On our small planet, we have built archives, libraries, and data centers to store the knowledge we have painstakingly accumulated. The data from 3I/Atlas is now a part of this planetary memory. In the distant future, if our species survives and travels to the stars, we will carry this memory with us. We will tell the story of the strange interstellar visitor that passed through our system at the dawn of our space age. It has become a part of our shared identity, a defining moment in our journey from a planetary to a galactic awareness. Let us return to the idea of the cosmic river of knowledge. This entire exploration has been a journey down that river. We have navigated its currents of data, its eddies of speculation, and its deep pools of philosophical reflection. The river does not end. It flows onward, towards a future of even deeper understanding. The mystery of 3I/Atlas is a new tributary that has joined this river, enriching it with new questions and new possibilities. Our task is simply to keep traveling, to keep our vessel of inquiry pointed forward, and to remain open and attentive to the wonders that the next bend in the river may reveal. The feeling that this mystery evokes is perhaps best described by the word sublime. It is the experience of being confronted by something so vast, so powerful, and so beautiful that it transcends our ability to fully comprehend it. This feeling is a mixture of awe and a strange, quiet joy. It is the joy of knowing that the universe is not a small, mundane place, but a place of infinite grandeur and profound, elegant mystery. The data from 3i/Atlas, in its beautiful ambiguity, has given us a direct and powerful connection to this sublime aspect of reality, a gift of pure and unadulterated wonder. This interstellar object has served as a cosmic Rorschach test. Some see in its strange chemistry the beautiful and unexpected creativity of nature. Others see the faint, ghostly trace of a distant intelligence. What we see in it is a reflection of our own intellectual and philosophical priors. The true value of the discovery is that it holds both of these powerful possibilities in a perfect, unresolved tension. It forces us to confront the vastness of both the natural universe and the potential for life within it. It is a mystery that expands our minds in two directions at once, pushing the boundaries of what we believe is possible. As our journey comes to a close, let the feeling of quiet contemplation settle. We have traveled far, from the intricate engineering of a space telescope to the very edges of our philosophical understanding. We have weighed the evidence, considered the possibilities, and embraced the profound beauty of a great scientific mystery. The questions raised by 3i/Atlas will linger in our collective consciousness, a gentle but persistent reminder of the vast and unknown universe that lies just beyond our familiar world. Let this not be a source of anxiety, but a source of deep and abiding peace. The universe does not owe us answers. It does not owe us companionship or meaning. It simply is. The meaning and the purpose we find are creations of our own consciousness, reflections of our own innate drive to explore and understand. The encounter with 3i/Atlas has been a powerful catalyst for this process of meaning-making. It has provided a focal point for our curiosity, a new chapter in our scientific story, and a new reason to look up at the night sky with a sense of hopeful and profound reverence for the grand, silent cosmos. We are the lucky ones. We are alive in the brief sliver of cosmic time when the tools to answer these age-old questions are finally being built. For millennia, our ancestors looked at the same stars and could only wonder. We are the first generation that can do more than wonder. We can measure, we can analyze, and we can begin to piece together the true story of our universe. This is a profound privilege and a great responsibility. It is our duty to continue this search with courage, with rigor, and with an enduring sense of humility before the magnificent complexity of the cosmos. The silence of space, once seen as empty, is now understood to be filled with a quiet, invisible traffic. Seeds of chemistry, and perhaps even of life, are constantly moving between the stars, weaving the galaxy into a single, interconnected whole. We are not an island, but part of a vast cosmic continent. The flight of 3i/Atlas through our small corner of the cosmos was a brief but powerful reminder of this fundamental connectedness. It has made the universe feel a little less vast and a little more like a neighborhood. Let us find comfort in the grand scales of time. The universe has unfolded over billions of years and will continue to do so for billions more. Our lives are a brief but brilliant flicker in that immense expanse. To be able to participate in this moment of discovery, to be able to contemplate our place in this ancient and ongoing story, is the gift of consciousness. The mystery of 3i/Atlas is a reminder to cherish this gift, to use our brief time to look outwards, to ask the biggest questions, and to appreciate the profound beauty and elegance of the cosmic context in which we find ourselves. This is the nature of true exploration. It does not always provide the treasure map with a clear X marking the spot. Sometimes, it provides only a strange and beautiful artifact, a single page from a book written in a language we do not yet understand. The value is not in the immediate translation, but in the patient, dedicated work of learning the new language. 3i/Atlas has given us a new cosmic language to learn, a language of exotic chemistry and anomalous physics. The process of deciphering it will be one of the great scientific adventures of the 21st century. Ultimately, the universe is a place of wonder. It is the source of the light we see by, the air we breathe, and the conscious minds with which we perceive it. It is not something separate from us. We are a part of it, a way for the cosmos to be aware of its own grandeur. The encounter with this interstellar messenger has been a profound moment of this cosmic self-awareness. It has held up a mirror and shown us the depth of our own curiosity, the power of our own intellect, and the unending beauty of the great, silent mystery from which we have all emerged. So let us rest here, at the end of our journey, in a state of informed awe. We have not found a simple solution, but something far more valuable, a deeper and more nuanced appreciation for the magnificent complexity of the cosmos. The strange gas cloud around 3I-ATLAS has expanded the horizons of our science and our philosophy. It has reminded us that the universe is under no obligation to be simple, and that the greatest discoveries often lie waiting in the subtle anomalies that defy our expectations. The journey to understand it has only just begun. The stars will continue their silent, wheeling dance across the night sky, just as they have for eons. Comets and asteroids will continue their lonely journeys through the dark. And we, on our small blue world, will continue to look up, to wonder, and to build our instruments of seeing. The encounter with 3I-ATLAS has enriched this ancient human tradition, adding a new layer of mystery and possibility to the night sky. The darkness is not an absence of light, but the presence of questions waiting to be asked and discoveries waiting to be made. In the final analysis, the story of 3I/Atlas is a gentle reminder that the most profound experiences in life are not about finding all the answers, but about learning to live in a state of contemplative wonder with the questions. The universe is a magnificent, unfolding mystery, and our greatest privilege is to be here for a brief moment as conscious and curious witnesses. Look up. The silence is listening, and the story is just beginning.